Some mega projects are completed within months. But what if I told you there's projects that took multiple decades to complete? These projects were so complex, it was simply impossible to construct them any sooner. Let's find out why they were so impossible by showing you the longest construction projects in history and the expansive engineering behind them.
Every so often, a bridge goes up that's about more than just concrete and cables. It becomes a statement, a symbol of connection. And in the case of the Gordie Howe International Bridge, a long-awaited answer to a problem that had been frustrating two countries for decades. Stretching across the Detroit River, linking Michigan to Ontario, this bridge isn't just big. It's one of the longest cable-stayed bridges in North America, and easily one of the most significant pieces of binational infrastructure being built anywhere on the continent. What makes the Gordie Howe so fascinating isn't just its size or its elegant design, it's the sheer effort it took to make it happen in the first place. For years, traffic between Detroit and Windsor had relied almost entirely on the Ambassador Bridge, a privately owned structure that had become so overburdened and outdated that it regularly caused backups stretching for miles. And when you're crossing handles more than a quarter of all trade between the US and Canada, that kind of congestion isn't just annoying, it becomes a real economic vulnerability. So the idea was simple: build a second bridge, publicly owned, with modern capacity and streamlined customs to keep people and goods moving. But nothing about getting it built was simple. Political resistance, lawsuits, funding fights, and international negotiations dragged the project out for years. In fact, the only reason it finally got off the ground was because both governments, on both sides of the border, realized that the stakes were just too high to keep waiting. The supply chains that run through Detroit and Windsor aren't just local, they're critical for everything from auto manufacturing to agriculture. And the Gordie Howe Bridge is designed specifically to handle that scale, with separate lanes for commercial and passenger vehicles, brand new customs plazas, and direct freeway connections on both sides. From an engineering standpoint, the project is stunning. The main span stretches more than half a mile between two massive towers, which themselves rise nearly as tall as some downtown skyscrapers. And because the Detroit River is both a busy shipping lane and an international waterway, the bridge has to offer enormous vertical clearance without the use of any in-water supports, which means all that load has to be perfectly balanced through its cables, anchored by foundations buried deep beneath the riverbanks. It's one of those designs that looks graceful from a distance, but hides an incredible amount of technical muscle. And while construction is still wrapping up, the impact is already clear. Crews have reshaped entire neighborhoods, built new access roads, and installed the most advanced border control systems either country has ever used, all with the goal of making the border feel less like a bottleneck and more like a seamless connection point. The bridge is also being built with long-term resilience in mind, factoring in everything from heavy freight wear and tear to extreme weather and seismic forces. So when the Gordie Howe International Bridge finally opens to traffic, it won't just be another route on the map. It'll be the result of decades of waiting, fighting, planning, and engineering. And it'll stand as a monument to the idea that sometimes the biggest challenges require the boldest solutions, especially when they span a river, a border, and 100 years of history. The High-5 Interchange in Dallas is one of those pieces of infrastructure that almost feels like a sculpture made out of concrete and steel. Rising more than 100 feet above the ground, where Interstate 635 meets US 75, it's an enormous tangle of ramps, columns, and sweeping curves that somehow fit together into one perfectly functioning machine. To the drivers who use it every day, it's just part of the commute. But to engineers, it's one of the most ambitious highway interchanges ever built in Texas. The name High-5 comes from the fact that it stacks 5 separate levels of traffic on top of each other. It's not just wide, it's vertical. Each layer handles a different movement of vehicles weaving together north-south and east-west traffic without the stop-and-go chaos that used to define this stretch of road. Before the rebuild, this intersection was a nightmare of congestion, one of the worst in the state. Thousands of cars squeezed through narrow cloverleaf ramps that couldn't handle modern traffic volumes, and the backup stretched for miles in every direction. When the Texas Department of Transportation decided to fix it, they didn't just widen lanes, they completely reinvented the interchange. The project called for nearly 3 million cubic yards of earthwork, more than 300,000 square feet of retaining walls, and an intricate arrangement of flyovers and bridges supported by over 30 massive piers. At its highest point, the top level rises roughly 12 stories above the ground, giving drivers a panoramic view of North Dallas as they sweep across in long elevated arcs. The engineering challenge was enormous. The construction had to be done while keeping traffic flowing through one of the busiest intersections in the region. Crews worked in carefully staged phases, shifting traffic patterns as new sections were built and old ones demolished. It was a kind of logistical ballet. Massive cranes lifting girders over live traffic, concrete pours happening overnight, and constant coordination to avoid shutting down major lanes during peak hours. What makes the High 5 interesting is how it manages to feel both efficient and elegant. The ramps curve smoothly, the columns are clean and evenly spaced, and the whole structure seems to float in the air instead of simply stacking slabs on top of one another. The geometry was refined through computer modeling to make sure every line of sight, merge point, and turning radius worked at highway speeds. It's a balance between engineering precision and visual clarity, something that's not easy to pull off at this scale. When it opened in the mid-2000s, the interchange immediately transformed the area. Traffic flow improved dramatically, cutting commute times and boosting development along both corridors. Businesses and residential complexes started rising nearby, drawn by the accessibility that came with a fully modernized highway system. For Dallas, it became a symbol of how serious the city was about mobility and infrastructure, an unmistakable reminder that this is a place built around movement. The TV Tower in Berlin, Germany, an iconic symbol of the city's skyline. Officially known as the Berliner Fernsehturm, this towering structure rises to 368 meters, making it the tallest structure in Germany and the fourth tallest in Europe. The idea of the Berlin TV Tower was conceived during the height of the Cold War, a period marked by the ideological battle between the East and West. Construction began in 1965 under the direction of the German Democratic Republic. The goal was to create a structure that would showcase German technological intelligence and broadcast television signals across the country. Interestingly, the original plan was to build the tower in the Müggelberger Hills, but this location posed safety risks for nearby Schönefeld Airport. Resultantly, the government, led by Walter Ulbricht, decided to relocate the project to Alexanderplatz, right in the heart of East Berlin. After 4 years of rigorous construction, the tower was completed in October 1969, just in time for the 20th anniversary celebrations of East Germany. The Berlin TV Tower is a masterclass in engineering. Built using reinforced concrete and steel, it features a sleek cylindrical shaft topped with a striking steel sphere. The sphere houses an observation deck at 203 meters and a revolving restaurant named Sphere, located just above. The restaurant makes a full rotation every 30 minutes, offering diners a panoramic view of Berlin without leaving their seats. The design of the tower was influenced by Soviet modernist architecture, aiming to reflect the ideals of progress and modernity. Its robust structure was engineered to withstand extreme wind conditions and even seismic activity, ensuring longevity and safety. The Berlin TV Tower cost over $70 million to build, which was 4 times more than the original budget. Despite being a symbol of secular, socialist East Germany, the tower has an ironic twist in its legacy. When sunlight hits the steel sphere, It reflects a giant cross, much to the embarrassment of the atheist East German government. Berliners humorously named this phenomenon the Pope's Revenge, suggesting that religion had left its mark on the most prominent structure in East Berlin. Today, the Berlin TV Tower is one of the most visited landmarks in Germany, attracting over 1 million visitors annually. But just wait until you hear about the Replacing the Chain of Rocks Bridge begins with one of the most intricate planning stages in river bridge engineering. Designing a structure that can be built in parallel with an existing crossing while maintaining navigational clearance for Mississippi River traffic. Survey crews first conduct hydrographic mapping of the river channel, charting depths, sediment patterns, and current velocities. This data informs the placement of piers, ensuring they rest on stable strata while minimizing interference with the river's navigation lanes. Because the Mississippi's flow and sediment load are constantly shifting, engineers must also anticipate future scour conditions and integrate protective measures into the foundation design. The foundation work starts with massive cofferdams or drilled shaft platforms, depending on the pier location. In deeper water, large steel caissons are floated into place, sunk to the riverbed, and filled with concrete to form the pier bases. Each pier is built up from reinforced concrete, with embedded anchor points for the steel superstructure. At the same time, temporary work trestles extend from the shore to give cranes and crews safe access over the water. This staging infrastructure must be robust enough to handle heavy steel girder lifts while withstanding the river's seasonal flooding and ice flows. The superstructure erection follows a highly choreographed sequence. Large structural steel sections are fabricated off-site, trucked or barged to the side, and then lifted into position using floating cranes capable of handling hundreds of tons. To reduce midstream lifting complexity, some spans are assembled on barges and floated into position before being jacked up onto their bearings. Each connection is made with precision-drilled bolt patterns and often supplemented with field welding. All steel receives multiple coats of protective paint to guard against corrosion in the river's humid and industrial environment. Approach spans and ramps tie the main bridge into the surrounding highway network. Earthwork teams construct approach embankments using compacted granular fill with retaining walls where the grade changes abruptly. The deck construction involves placing stay-in-place forms or removable falsework, followed by pouring a high-strength concrete slab over the steel girders. Expansion joints and bearings are carefully installed to accommodate thermal movement, while drainage scuppers ensure rainwater is directed off the deck and away from structural steel. Because this is a replacement project, demolition of the old bridge becomes its own engineering challenge. The sequence is planned so that no debris falls into the navigation channel, often requiring controlled lowering of sections onto barges. In some cases, explosives are used to drop spans in a controlled manner onto prepared mats in the water, with immediate recovery of all material. Steel is salvaged and recycled, while concrete is processed for reuse as aggregate in other projects. Rather than originating from a single excavation point, the Ontario Line subway project in Toronto is unfolding simultaneously across multiple zones, each with distinct geotechnical profiles, construction constraints, and staging challenges. This complex, phased approach is dictated by the nature of the line itself, a hybrid system incorporating underground tunnels, surface-level alignments, and elevated guideways, all within a dense urban environment with deeply entrenched infrastructure. The underground segments begin with launch shaft construction, typically established in large open-cut excavations. These shafts are stabilized with secant pile walls or soldier pile and lagging systems, supported by steel struts or tiebacks to resist lateral soil pressures. Excavation descends in stages to reach the tunnel invert elevation, where tunnel boring machines are then assembled and launched. Each TBM is equipped with an earth pressure balance or slurry shield, depending on soil conditions, allowing it to navigate soft soils, mixed face conditions, and glacial till while maintaining face stability. Tunnel lining is performed immediately behind the TBM's cutting head using precast concrete segments. These segments are gasketed and bolted to form a watertight ring, which becomes part of the permanent tunnel structure. The logistics of segment delivery, spoil removal, and TBM maintenance are coordinated from surface-level support sites, which include slurry processing plants, muck storage, and concrete casting yards. At intermodal stations like Exhibition, Osgood, and Queen, massive excavation pits are established using a top-down or cut-and-cover method. These stations interface with existing subway lines and utility corridors, necessitating complex underpinning of adjacent buildings, and the use of ground freezing or jet grouting to control groundwater inflow. Temporary decking allows surface roads to remain operational while deep excavation continues below. Internal strutting systems are critical to maintain the integrity of the excavation, particularly for multi-level station boxes with mechanical, ventilation, and emergency egress spaces. Above ground, elevated guideways are constructed using precast segmental construction or cast-in-place concrete methods. These viaducts require column piers with deep foundations, often drilled caissons or driven piles, to ensure stability in areas with compressible soils or fluctuating groundwater. Segments are lifted using launching gantries or segment lifters, then post-tensioned together to form continuous spans. Alignment tolerances are extremely tight to maintain ride quality and track geometry. Track installation across the entire line incorporates both direct fixation systems and traditional ballast and tie methods, depending on location. In tunnels, low-vibration track slabs are installed using high-strength concrete over a waterproofed base. Track work includes rail anchors, expansion joints, and insulated rail fasteners, all designed to meet noise, vibration, and thermal movement requirements. A substantial portion of the Ontario line's complexity comes from its integration with live transit corridors, roadways, and utility networks. This involves ongoing utility relocations, including water mains, high-voltage cables, and telecommunications lines, all done with extensive traffic staging and night shifts to reduce surface disruptions. Monitoring of existing structures is continuous, using inclinometers, strain gauges, and real-time survey systems to detect any movement induced by construction activities. Most people think of Seattle and picture coffee, tech companies, and rainy skylines. But underneath all of that, there's been this slow-burning struggle to build a transit system worthy of the region's size, growth, and ambition. That's where Sound Transit 3 comes in. It's not just another local project, it's one of the largest transit expansions in the country. And it's meant to completely transform how people move across the entire Puget Sound region, not just today, but for generations to come. What makes Sound Transit 3 so different is the sheer scale of it. We're talking about over 60 new miles of light rail, pushing far beyond the current network, and reaching deep into communities that have long been isolated by traffic or dependent on slow buses and crowded highways. From Everett in the north to Tacoma in the south, and all the way out to places like Redmond and Issaquah, this is about stitching together an entire metro area with a spine of reliable, fast rail service that doesn't get stuck in traffic and doesn't rely on the constant expansion of roads. But it's not just about light rail. This package includes new bus, rapid transit lines, expanded commuter rail, more park and ride facilities, and even better, bicycle and pedestrian connections that feed into the bigger system. It's a kind of all of the above strategy that recognizes how sprawling and geographically complicated this region really is, with mountains, lakes, and waterways that make every mile of infrastructure harder to build and more expensive to maintain. And that's part of what makes this project so fascinating. Because it's not easy, and the engineers and planners behind it are constantly balancing cost, complexity, and community needs in ways that few other cities have to deal with. Some of the most challenging parts are the tunnels. Building rail through central Seattle means going underground, and that means tunnel boring machines, deep excavation, and seismic design that can withstand the reality of living in an earthquake zone. Then there are the floating bridges. Yes, actual floating rail lines over water, which bring a whole new set of engineering puzzles, like how to keep railcars stable on a structure that literally moves with waves and weather. Every piece of this system has to be custom fit to the landscape, and that's why timelines stretch into the 2030s and beyond. What really drives Sound Transit 3, though, isn't just congestion relief. It's about shaping the future of how the region grows. With light rail stations comes development, density, and the chance to build neighborhoods around transit instead of highways. It's a blueprint for how to grow without choking on gridlock. And while it comes with a hefty price tag, voters backed it because the alternative was worse. A future where commutes get longer, emissions keep rising, and the economy starts to buckle under its own weight. Gardens, where a brand new urban heartbeat is under construction. Located in the heart of Miami-Dade County, this mega project is transforming 200 acres of unused land into a dynamic, mixed-use destination. The project was first proposed in 2018 as part of the city's broader push for economic revival and cultural visibility. After years of planning, groundwork officially began in late 2021, and currently the site is buzzing with activity. The planned Miami Gardens City Center is a large, mixed-use development featuring entertainment, restaurants, residential units, hotels, and more, with a focus on catering to tourists and residents alike, including a 50,000 square foot dinner show. The budget is estimated to be around $650 million. That money is being invested in phases with different developers handling the commercial, residential, and recreational elements. In its current phase, construction crews are building luxury apartments, a shopping promenade, and a central plaza. The design includes green rooftops, solar energy systems, and water-smart landscaping, making it one of the most eco-conscious urban projects in Florida. For decades, Miami Gardens has struggled with limited economic growth, despite being home to iconic locations like Hard Rock Stadium. The new city center will bring in retail chains, locally owned businesses, and high-end restaurants, helping to keep tourism alive in the community. It will also provide more than 2,000 jobs in the next 2 years, both in construction and post-completion retail, hospitality, and maintenance roles. The architecture blends modern glass structures with open-air courtyards and pedestrian-friendly boulevards. The construction involves tilt-up concrete panels, modular steel frames, and rapid-setting concrete mixers to stay on schedule. Tower cranes and automated rebar tying robots help speed up vertical construction. Underground workers are laying down a state-of-the-art fiber optic backbone that will support everything from smart lighting to Wi-Fi zones and security systems. This tech will allow residents and visitors to navigate the city center with real-time information on parking, traffic, and events. The landscape plan is even impressive. Over 1,000 trees will be planted, many of them native species that support the fragile ecosystem in Florida. Bioswales and rain gardens are being added to naturally filter stormwater and reduce runoff. By 2027, the Miami Gardens City Center will be fully operational. But even in 2025, it's already reshaping the skyline. Residents who've lived in the area for years are seeing the future unfold right outside their windows. Let's move over to another giant transformation in Tampa, the I-275, quite like the Portal North Bridge replacement. This vital link over the Hackensack River in New Jersey, a bottleneck for both commuter and intercity rail, required a complete structural and operational transformation. The original swing-span bridge, built in the early 1900s, was not only mechanically outdated, but also posed significant operational constraints due to its low vertical clearance and movable span that had to open for marine traffic. The replacement structure addresses these issues through a fixed span design elevated high enough to accommodate river navigation without disrupting rail service. Construction began with site access improvements, including utility relocations, staging platform installation, and the construction of temporary trestles to allow cranes and materials to move efficiently across the tidal wetlands. The geotechnical profile of the area necessitated deep foundation work. Driven steel H-piles and drilled shafts were used to create load-bearing capacity within the soft riverine sediments. Vibratory hammers and impact pile drivers were employed, with real-time monitoring to reduce vibration transmission to nearby rail operations and residential structures. The new bridge structure consists of a series of through-girder spans made from weathering steel, designed to resist corrosion in the harsh marine atmosphere. Prefabricated girder segments were shipped to the site by barge, hoisted into position by floating cranes, and spliced using field-welded connections. These spans rest on reinforced concrete piers constructed using cofferdams in the riverbed. The cofferdams were dewatered, then excavated and filled with tremie concrete to form seal slabs before pier shafts were cast in place. Reinforcement cages for the piers were assembled off-site and lowered into place using heavy lift cranes. Track systems were constructed on ballastless deck slabs using direct fixation fasteners to reduce track vibration and long-term maintenance needs. Each track was aligned to extremely tight tolerances, critical for maintaining the high-speed rail standards of the corridor. New overhead catenary systems were installed, with mast foundations constructed in parallel with the substructure work. These systems included constant tension mechanisms to accommodate thermal movement, ensuring uninterrupted power delivery to electric locomotives. To minimize service interruptions on the Northeast Corridor, much of the bridge's integration work was conducted during night and weekend outages. Existing signal and interlocking systems had to be reprogrammed, with new cabling, relay cases, and fiber connections installed alongside the structure. Signal cutovers and testing followed Federal Railroad Administration protocols to ensure full system compatibility and safety. The project also required environmental mitigation measures, especially related to aquatic habitat and wetland disturbance. Silt curtains, turbidity monitoring, and fish migration scheduling were all part of the compliance framework. Additionally, the construction team coordinated with the Coast Guard to ensure navigational access was maintained during critical phases of in-water work. In the construction of high-rise structures like the Waterline Tower, vertical integration is the principal logistical and engineering challenge. We have to talk about the Ping An Finance Center in Shenzhen, China, towering at a breathtaking 599 meters. This mega project stands as the second tallest building in China and the fifth tallest in the world. Completed in 2017, this skyscraper is a symbol of the rapid economic growth of China and the emergence of Shenzhen as a global financial powerhouse. The Ping An Finance Center reaches 115 floors above ground with an additional 5 basement levels, offering a total floor area of approximately 620,000 square meters. It houses office spaces, a luxury 5-star Park Hyatt hotel, a high-end shopping mall, and an expansive conference center. A standout feature is the free sky observation deck on the 116th floor, perched at 562.5 meters, one of the highest observation decks globally, offering 360-degree panoramic views of Shenzhen and even Hong Kong on clear days. The sleek, modern facade of the skyscraper is clad in 1,700 metric tons of stainless steel, providing both aesthetic elegance and durability against the humid climate of Shenzhen. The structure employs a mega-braced frame system combined with a high-strength steel core. This ensures resilience against strong typhoons and seismic activity, both common in the region. The Ping An Finance Center showcases cutting-edge construction techniques. Its superstructure is supported by 8 massive steel columns, tapering as they ascend, from dimensions of 6 by 3.2 meters at the base to 2.9 by 1.4 meters at the top. This design optimizes load distribution and stability. The building is also equipped with 33 double-deck elevators capable of reaching speeds up to 10 meters per second, swiftly transporting occupants to their desired floors. The foundation consists of deep-set piles, ensuring stability even in the challenging soil conditions of Shenzhen. Interestingly, the original design included a 60-meter antenna that would have made it taller than the Shanghai Tower. However, this plan was scrapped in 2015 due to concerns about potential interference with flight paths in the area. Built with around $13.5 billion, the Ping An Finance Center is a vital economic hub in one of the most dynamic cities in China. It also serves as a focal point for international business, attracting major corporations, luxury brands, and global investors. But we have to talk about, beginning not with the terminal itself, but with the challenge of location, the LNG Canada project had to contend first and foremost with the complex coastal environment of Kitimat, British Columbia. Positioned at the head of the Douglas Channel, the site required substantial groundwork before any liquefaction equipment could be installed. Tidal fluctuation, seismic resilience, and marine access all factored into the foundational decisions. Site preparation included extensive dredging to deepen the berthing areas for LNG carriers, as well as grading and surcharging to stabilize the reclaimed land that would support the terminal's heaviest modules. Early civil works were dominated by the construction of an access road network and a temporary construction village to house thousands of workers. Simultaneously, the site was divided into key zones for utilities, process trains, storage tanks, and marine infrastructure. Earth-moving operations brought in millions of cubic meters of gravel and engineered fill to meet precise compaction and elevation standards, taking into account long-term settlement and flood risk from both terrestrial and marine sources. A robust drainage system was installed to manage stormwater runoff and control erosion, especially given the region's high annual rainfall. In parallel with ground stabilization, pile driving began for the key process and storage areas. Steel piles, some driven over 30 meters deep, were installed using impact hammers and vibratory rigs, creating a dense grid to support the immense static and dynamic loads from the cryogenic liquefaction trains. These trains, each comprised of prefabricated modules weighing hundreds of tons, were transported to site on heavy lift vessels and positioned using self-propelled modular transporters. Each module included components such as heat exchangers, compressors, and flaring systems, which had to be precisely aligned and connected to the plant's process piping. At the heart of the facility, the liquefaction units operate using a dual mixed refrigerant process, chosen for its efficiency in converting natural gas into a supercooled liquid at approximately minus 160 degrees Celsius. The engineering behind this required intricate thermal insulation, cryogenic piping, and high-capacity heat exchangers. All systems had to be rigorously tested for leaks and thermal integrity, with cold commissioning involving controlled cooling cycles and nitrogen purging before live hydrocarbons were introduced. The marine terminal, a critical element of LNG Canada, was engineered to accommodate some of the largest LNG carriers in the world. Construction included a trestle-supported jetty, loading arms with swivel joints capable of transferring LNG at high flow rates, and emergency shutdown systems integrated with both the vessel and terminal controls. The jetty itself required hundreds of precast concrete deck panels supported by driven piles and was built in a modular fashion to accelerate schedule efficiency. Integration of the plant's utilities, including power generation, water treatment, and flare systems, was another major effort. The facility features its own electrical substation and backup power units to ensure uninterrupted operations. Because of the facility's environmental commitments, flaring is minimized through a closed-loop design that recycles boil-off gas and prevents atmospheric release wherever possible. Not many projects in New York can claim they were first proposed during the Great Depression and still didn't see the light of day until the 21st century, but the Second Avenue subway wears that badge like no other. This wasn't just a transit line, it was a promise, passed from one generation of New Yorkers to the next, that one day, maybe, the city's most crowded corridor would finally get the relief it deserved. And after nearly a century of delays, cancellations, and false starts, the first phase finally opened in 2017, turning a long-running urban myth into a real, functioning piece of infrastructure. What makes this project so unique isn't just how long it took, but what it had to fight through along the way. The Upper East Side of Manhattan has always been one of the densest residential neighborhoods in the city, but for decades it had just one subway line, the Lexington Avenue line, doing the heavy lifting for hundreds of thousands of commuters every single day. Trains were jam-packed, platforms were bursting, and yet the idea of carving out a new subway down 2nd Avenue always seemed just out of reach. Every time funding was close, something went wrong. A war, a recession, a bankruptcy. Plans would be drawn, environmental reviews would begin, ceremonial groundbreakings would be held, and then the whole thing would collapse again. Rinse and repeat. When construction finally did begin for real, in the mid-2000s, it was no small feat. Digging tunnels through the bedrock of Manhattan is already complicated, but doing it under active streets, dense buildings, and some of the highest real estate values in the country raises the stakes to an entirely different level. Tunnel boring machines had to snake their way beneath existing infrastructure while crews managed utilities, avoided gas lines, relocated water mains, and stabilized buildings that were never designed to sit above a 21st century subway excavation. And then came the stations, not simple stops, but massive, cathedral-like caverns carved out of solid rock, deep beneath the surface. Each one had to be built with enough space to handle modern train volumes, with high ceilings, full accessibility, climate control, and finishes that actually made them feel like places people wouldn't mind spending a few minutes each morning. It was expensive, it was slow, but it was a level of attention to detail that set a new standard for American transit construction. When the first phase finally opened, running from 96th Street down to 63rd, it immediately started pulling riders off the Lexington line, easing crowding and proving that yes, the 2nd Avenue subway could work. But the job's not finished. Not even close. The full vision calls for extending the line all the way down through Midtown, the East Village, and into the financial district, creating a true second spine along Manhattan's east side. The next phase is already in motion, inching southward, and while the pace might still feel glacial, each new tunnel is another step toward finishing the job New York started almost 100 years ago. So the 2nd Avenue subway isn't just a train. It's a symbol of persistence, of finally delivering on a promise that should have been kept long ago. It shows what happens when a city refuses to give up, even if it takes an entire lifetime to get it done. There's something about the Dallas-Fort Worth area that never stops growing. Roads stretch wider, suburbs push further, and every year it feels like the region adds another layer of sprawl. But as the population surges and more cars hit the road, that old Texas strategy of just adding another lane isn't cutting it anymore. That's why the Southeast Connector project stands out, not just as another highway expansion, but as a massive, coordinated effort to untangle one of the most congested and complicated corridors in North Texas. If you've ever tried to drive through the southeast side of Fort Worth, especially during rush hour, you already know the pain points. Narrow lanes, outdated interchanges, and bottlenecks where 3 major highways collide. This is where I-20, I-820, and US 287 all come together, carrying everything from daily commuters to heavy freight. The volume is intense, and the existing infrastructure simply wasn't built to handle this kind of load. So instead of another patch job, TxDOT went big, with a full-scale reconstruction of over 16 miles of highway, rebuilding bridges, reconfiguring interchanges, and modernizing everything from pavement to storm drains. But this isn't just about traffic flow. It's about safety, too. The current configuration is full of sharp curves, short merging lanes, and weird transition points that make it one of the more accident-prone areas in the region. Part of the Southeast Connector's mission is to eliminate those hazards entirely, replacing outdated designs with smoother geometry, better sightlines, and wider shoulders that give drivers more room to breathe. It's the kind of redesign that doesn't just speed things up, it actively saves lives. One of the most impressive aspects of the project is the sheer amount of work being done at once. This isn't a staged wait-and-see approach. It's an all-in, all-at-once operation. Crews are demolishing and rebuilding dozens of bridges, adding collector-distributor roads to separate through traffic from local exits, and widening lanes across the board to support long-term growth. And because this corridor is such a critical freight route, the new design will allow for a smoother flow of trucks, helping to unclog the supply chain and reduce delays that ripple far beyond DFW. Construction, of course, is never simple. There are major utility relocations, environmental protections for nearby creeks, and traffic management plans that have to keep thousands of vehicles moving even while everything is being rebuilt around them. It's like renovating a house while still living in it. Only the house is on fire and the kitchen is full of semis. But despite the challenges, progress is steady, with massive earth-moving equipment, steel girders, and towering cranes shaping a corridor that's going to look and function completely differently once it's done. In a region defined by cars, roads, and relentless growth, the Southeast Connector isn't just another construction zone. It's the blueprint for how North Texas plans to keep moving forward. And when it's finished, drivers won't just feel the difference. They'll see it in the form of safer ramps, shorter commutes, and the kind of infrastructure that finally catches up to the pace of the place it serves. So solar farm, and this one's a major step forward for clean energy in Florida. Located in Blodgett, just outside of Tallahassee, the Keelso Solar Farm is a massive renewable energy project aiming to power tens of thousands of homes without burning a single ounce of fossil fuel. The farm will cover over 3,000 acres of land and feature more than 800,000 solar panels. When fully operational, it's expected to generate 300 megawatts of electricity, enough to power about 60,000 homes. That's a huge deal for a state that relies heavily on natural gas, and where demand for electricity keeps rising year after year. The Keelso Solar Farm is using some of the most advanced solar technology available. Each panel is mounted on a single-axis tracking system that follows the sun across the sky. This means more sunlight captured, more power generated, and higher efficiency all day long. These trackers are operated by AI-based control systems that adjust in real time based on cloud cover, shading, and even bird activity. Crews on site are using automated pile drivers to install the support beams into the ground with laser precision. Once installed, robotic arms place the panels, reducing the risk of damage and speeding up the entire process. The wiring infrastructure is massive too. Miles of underground cabling are being installed using plow trenches, ensuring that the landscape remains as untouched as possible. The system is being built with high voltage inverters, battery storage units, and smart grid connectivity that allows the power to flow instantly when needed. The battery storage component is another highlight. Keelso Solar Farm will have 120 megawatt hours of battery capacity, allowing it to store energy during the day and feed it back into the grid at night. That's crucial for balancing Florida's energy load and preparing for peak demand times. The budget for this project is close to $500 million, funded through a mix of private investment and green energy incentives provided by the state and federal governments. Construction began in 2023, and currently the farm is about 70% complete. Rows of solar panels already stretch to the horizon, and the control center is being built with sustainable materials, including recycled steel, solar roof tiles, and rainwater harvesting systems. Let's move over. A massive rail yard into a walkable, mixed-use urban district is a construction undertaking that combines demolition, structural engineering, and urban infrastructure on a scale rarely seen within the core of a major American city. Centennial Yards in downtown Atlanta is a prime example, involving the redevelopment of former gulch land, an underutilized expanse of sunken rail corridors and viaducts, into a vibrant network of buildings, roads, and public spaces layered both vertically and horizontally. The site's existing condition presented immediate challenges. Large portions of the project footprint sit below street grade, surrounded by elevated roadways and crisscrossed by active rail lines. To establish a new ground level suitable for pedestrian circulation and vehicle access, construction crews first had to implement structural deck systems over sections of the gulch. These concrete and steel platforms, supported on new pile foundations, create an artificial surface that connects to existing streets via ramps and vertical cores, while spanning over active rail infrastructure below. Before those platforms could be built, crews performed selective demolition of obsolete concrete retaining walls, drainage structures, and derelict freight infrastructure. Simultaneously, extensive underpinning and structural reinforcement were carried out on adjacent viaducts to preserve structural integrity during nearby excavation and pile driving. Soil nailing and shotcrete were used on vertical cut faces to maintain stability, especially in narrow work zones, where deep excavation was required next to functioning roadways. As the platform structures took shape, the installation of new utilities proceeded in parallel. Stormwater drainage systems were installed beneath the platform decks using precast concrete pipes and box culverts, routed toward detention vaults and outfalls, capable of handling peak flow from large roof areas and paved surfaces. Domestic water, fire protection lines, electrical duct banks, and fiber conduits were all routed through newly constructed utility corridors, integrated with service cores that penetrate the platform deck and provide vertical circulation and access. With the new artificial grade in place, above-grade vertical construction could proceed. Foundations for the buildings included deep, drilled piers extending through the deck system into stable substrata. Structural steel framing, composite concrete decks, and curtain wall systems were erected using tower cranes mounted on temporary footings above the platform. Mechanical systems, such as air handling units, cooling towers, and electrical switchgear were installed in shared utility basements located between buildings, designed for centralized operation and future capacity expansion. The layout of Centennial Yards required tight geometric coordination between new construction and existing urban elements. Street alignments, bridge connections, and pedestrian access points had to match the city's existing grid while introducing new mobility elements like bike lanes, wide sidewalks, and mass transit access. Specialized paving systems were used on pedestrian corridors, including permeable pavers and decorative concrete tied into tree wells and biofiltration zones for stormwater treatment. At the Margaret Hunt Hill Bridge is one of the most recognizable landmarks in Dallas, a structure that turned what used to be an ordinary river, crossing into a signature symbol of the city. Stretching across the Trinity River, just west of downtown, it's a piece of infrastructure that became art, an unmistakable white arc rising high over the floodplain, pulling the skyline and the river together in a single dramatic line. When it opened, the bridge immediately changed how people thought about Dallas. For decades, the Trinity River had been treated as a kind of boundary, a place that divided downtown from the neighborhoods on the other side. The bridge turned that division into a connection. Suddenly, crossing the river wasn't just a commute, it was an experience. The single, massive steel arch at the center became the defining feature, rising nearly 400 feet into the air and holding up the deck below with a series of taut, graceful cables that seemed to hang like strings on an instrument. The design came from Santiago Calatrava, the Spanish architect and engineer known for his sculptural bridges around the world. He was brought in to help reimagine Dallas's Trinity Corridor, and the Margaret Hunt Hill Bridge was the first of his works to actually rise from that plan. It carries Woodall Rogers Freeway across the river, but calling it just a highway bridge doesn't do it justice. It's both functional and expressive, a kind of white ribbon that ties together two halves of a city that had long turned its back on the river. Structurally, it's a marvel of engineering precision. The arch doesn't sit directly over the roadway, it soars above it, leaning forward in a way that makes the cables fan out asymmetrically toward one side. This off-center suspension system was a huge technical challenge. Every load had to be calculated down to the smallest detail to make sure the deck stayed balanced, even though the support comes from only one side. The arch itself was fabricated from steel sections that were shipped in and welded together on site, each one shaped with incredible accuracy to keep the curve continuous from the base to the crown. During construction, the site of the arch rising over the Trinity became a local event. For months, it stood half-finished, waiting for the final sections to be lifted into place, and people would drive out just to watch it take shape. When it was completed, it instantly became part of the city's visual identity, appearing on postcards, logos, and countless skyline shots. But what makes the bridge more than a photo opportunity is what it represents. It was part of a larger plan to revitalize the Trinity River corridor, to turn flood control levees and neglected land into parks, trails, and public spaces. The bridge became the physical and symbolic gateway to that transformation. Even as debates continue about how to develop the riverfront, the Margaret Hunt Hill Bridge stands as proof that the city can think on a grand scale and actually pull it off. The iconic Burj Khalifa in Dubai, towering at an unbelievable 828 meters, it holds the title of the tallest structure in the world. Originally named the Burj Dubai, construction began on January 12, 2004, and was officially completed on January 4th, 2010. However, during its inauguration, the name was changed to Burj Khalifa in honor of Sheikh Khalifa bin Zayed Al Nahyan, the former president of the UAE. His financial support helped Dubai during the 2008 financial crisis. This change reflected the collaboration and resilience of the UAE during tough times. The Burj Khalifa was designed to be the centerpiece of downtown Dubai, a large-scale, mixed-use development featuring residential towers, hotels, parks, and the Dubai Mall. The idea was to shift the economic focus of Dubai from oil to tourism and services, putting the city on the global map as a symbol of modernity and luxury. Burj Khalifa draws inspiration from Islamic architecture, particularly the spiral minaret of the Great Mosque of Samarra. Its Y-shaped floor plan optimizes residential and hotel space, while providing structural stability against strong winds and seismic activity. The tower features 163 floors above ground and 2 basement levels, with amenities ranging from luxurious apartments, corporate suites, the Armani Hotel, and world-class restaurants. Its sleek facade is covered with over 26,000 glass panels designed to withstand extreme heat and intense sunlight in Dubai. Constructing the Burj Khalifa was no small challenge. The primary structure consists of reinforced concrete with the spire made from structural steel. Over 330,000 cubic meters of concrete and 55,000 tons of steel rebar were used, requiring innovative engineering solutions. The foundation comprises 192 reinforced concrete piles, each buried more than 50 meters deep to support the immense weight of the building. One of the biggest challenges was pumping concrete to such unprecedented heights. The project set a world record for the highest vertical concrete pumping at 606 meters. To manage the desert heat, concrete was poured at night with ice added to the mix, preventing cracks during curing. The total cost of construction was around $1.5 billion, a massive investment that has paid off through tourism, business, and real estate. However, the race to build the tallest skyscraper is far from over, with several mega towers under construction or proposed that will redefine city skylines. The most anticipated project is the Jeddah Tower in Saudi Arabia, designed to surpass the Burj Khalifa and become the first building to reach 1,000 meters. Originally planned for completion in 2020, the project faced delays but resumed construction in 2023 under a new contractor, with expectations to finish in the coming years. Dubai Creek Tower is another record-breaking futuristic structure, estimated to reach 1,300 meters. If completed, it would dethrone every existing skyscraper. However, this Emaar-backed project remains on hold, with construction stalled since the pandemic. China is also competing in the height race with the Suzhou Zhongnan Center, planned for 729 meters. Greenland Jinmao International Financial Center is another skyscraper, 499 meters high under active construction, along with the proposed KL Tower in Malaysia, 644 meters in height. Whether one of these towers will surpass the Burj Khalifa remains to be seen, but the next world's tallest building is already rising. In the case of the Nashville International Airport New Horizon Expansion, the work unfolds as a multi-phase effort designed to keep the airport fully operational, while substantially increasing capacity and modernizing its infrastructure. Initial activity begins with airfield and terminal area surveying, establishing precise reference points so that new construction ties seamlessly into existing taxiways, runways, and concourses. Given the tight geometry of active airside zones, staging areas for materials and equipment are carefully designated to avoid conflicts with aircraft movements and ground service operations. Earthwork and foundation operations for the terminal expansion start almost immediately after site clearance. Excavation crews remove unsuitable soils and place engineered fill, followed by deep foundation piling in areas where heavy superstructures such as multi-level concourses will rise. Concrete pile caps and grade beams are then cast to distribute loads from the terminal building's steel frame. Underground utilities are routed early in the process, including storm drainage systems, fuel hydrant lines, and large diameter chilled water piping for HVAC service. Structural steel erection is one of the most visible milestones. Steel columns and long-span roof trusses are lifted into position using crawler cranes, with connection bolts tightened to specification and every weld inspected. The roof structure for expanded gate areas must accommodate wide, column-free spans to allow unobstructed passenger circulation and clear sightlines to aircraft parking positions. Once the primary frame is complete, crews begin installing metal decking, followed by concrete slabs for the upper floors. Simultaneously, the terminal facade takes shape with curtain wall systems composed of insulated glass panels and aluminum framing. These assemblies are designed to maximize daylighting while meeting stringent acoustic requirements to reduce aircraft noise inside the building. Roof systems integrate both conventional weatherproofing membranes and provisions for photovoltaic panels in select zones. Interior build-out progresses in carefully coordinated stages. Mechanical systems are installed overhead, including large air handling units, ductwork, and high-efficiency chillers and boilers housed in mechanical penthouses. Electrical teams run conduit and pull wiring for lighting, communications, and security systems, ensuring redundancy for critical airport operations. Finishes follow: terrazzo flooring in high-traffic public zones, acoustical ceilings in passenger seating areas, and durable wall panels designed for ease of maintenance. One of the expansion's defining features is the upgrade to passenger processing areas. Baggage handling systems are expanded with high-speed conveyors, inline TSA screening stations, and integrated RFID tracking. Check-in halls are reconfigured for self-service kiosks and biometric boarding gates, all linked to the airport's IT backbone. Wayfinding signage and dynamic display boards are added to guide passengers efficiently through the expanded facility. Airside improvements are equally critical. New and reconfigured aircraft gates require concrete apron paving designed to withstand repeated loads from large commercial jets. Jet bridges are installed and tested for compatibility with multiple aircraft types, while fuel and ground power systems are extended to serve the added stands. Lighting upgrades improve apron visibility for nighttime operations, and advanced docking guidance systems help position aircraft with precision. Rather than beginning at a central hub or urban terminal, the Alto high-speed rail project's earliest fieldwork concentrated on corridor preparation through rural and semi-rural regions, where right-of-way acquisition and grading could proceed with minimal disruption. The rail line, intended to connect Toronto to Quebec City with ultra-fast, electrified service, required the creation of an entirely new grade-separated alignment, distinct from the existing freight-heavy rail network. This demanded comprehensive land surveying, geotechnical assessments, and environmental clearances across hundreds of kilometres before any civil works could start. Once alignment studies and land procurement were finalised, the corridor was divided into construction segments managed by multiple contractors. Earthworks commenced almost simultaneously across numerous stretches, involving topsoil stripping, subgrade stabilisation, and extensive cut and fill operations. In some areas, embankments rose over 10 metres high to maintain consistent gradient profiles, while in others, deep rock cuts were blasted to maintain design speed tolerances. Where the route intersected natural waterways or wetlands, precast culverts and multi-span bridges were installed, with sediment control measures and wildlife passages integrated into the design. One of the most technically demanding aspects was the track bed itself. High-speed rail demands extremely tight tolerances for vertical and horizontal alignment, necessitating a multi-layered track foundation system. Sub-ballast and ballast layers were placed over geotextile reinforced subgrades compacted to precise densities. In critical high-speed segments, especially on long straightaways or gentle curves, slab track systems were used instead of ballast, incorporating precast concrete panels anchored to reinforced concrete bases. These sections offered better long-term stability and reduced maintenance frequency, essential for sustaining speeds approaching 300 kilometers per hour. Electrification followed closely behind track installation. Overhead, catenary systems were constructed using regularly spaced mass, tensioning assemblies, and contact wire supports calibrated to minimize sway and maintain constant contact with the pantograph. Substations were placed at strategic intervals to step down transmission voltage and feed it into the overhead system. These were built on elevated pads and connected to regional grids through buried or overhead transmission lines, depending on terrain and corridor width. Stations along the Alto line featured a combination of central platform and side platform configurations, with full-length canopies, soundproofed glass walls, and automatic platform screen doors. Structures were built using steel frames and precast concrete panels to accelerate construction schedules and standardize elements across cities. At major urban terminals such as Montreal and Ottawa, new underground concourses and connection tunnels were excavated using a mix of cut and cover and tunnel boring techniques to integrate with existing transit networks. Control and signaling infrastructure represented a core component of the system's operational integrity. The Alto line uses a European train control system adapted for Canadian conditions, relying on continuous communication between trains and trackside balises to manage speed, spacing, and braking curves. Fibre optic cables were laid alongside the right-of-way, bundled with power and data conduits in armoured ducts, and routed through centralised equipment rooms for resilience and redundancy. Noise mitigation was essential throughout populated areas. This was addressed through the installation of acoustic barriers, vibration-isolated track beds, and embankment berms shaped to deflect sound. In addition, crossing eliminations were carried out at every road and rail interface, either through overpasses, underpasses, or full-grade separations, ensuring uninterrupted operation of the high-speed network. You could argue that no American infrastructure project has ever been more ambitious, more controversial, or more flat-out chaotic than the Big Dig. Officially known as the Central Artery/Tunnel Project, this wasn't just a highway job, it was a massive, decades-long attempt to untangle the concrete mess that had been strangling Boston for years. And in the process, it became one of the most complicated urban engineering efforts the country has ever seen. It all started with a problem that was painfully obvious to anyone who ever tried to drive through downtown Boston. The elevated I-93, known as the Central Artery, was loud, crumbling, overcapacity, and a complete urban barrier, dividing neighborhoods and jamming traffic so badly that rush hour could stretch for half the day. So the solution? Bury it. Not just cover it or reroute it, but actually dig a brand new expressway deep below the existing one, right through the middle of a dense, historic city that was still very much alive above ground. And that's where things got wild, because you don't just drop a tunnel under Boston. You have to work around centuries-old buildings, subway lines, sewer mains, water pipes, electrical conduits, and ground conditions that are half landfill and half riverbed. Crews had to excavate around live rail tunnels, underpin massive structures so they didn't collapse, and deal with groundwater constantly trying to flood the site. In some places, the only way to keep digging was to freeze the ground solid with liquid nitrogen so it wouldn't cave in. The main tunnel itself wasn't even the only part. There was also the Ted Williams Tunnel, stretching under Boston Harbor to link up with Logan Airport. That section used a technique called immersed tube tunneling, where pre-formed tunnel sections were floated out into the water, sunk into a dredged trench, and then connected underwater like pieces of a giant Lego set. And let's not forget the Zarkham Bridge, a massive cable-stayed structure that became the visual symbol of the entire project, spanning the Charles River and replacing the old, rusted-out expressway ramps that used to dominate the skyline. But for all its engineering brilliance, the Big Dig became equally famous for its cost overruns, delays, political fights, and even tragic failures. What started with an estimate in the billions ballooned into over $14 billion by the time it was done, and there were lawsuits, construction flaws, and public outrage along the way. At one point, a tunnel ceiling panel collapsed, killing a driver and shaking public confidence in the entire effort. It was a reminder that even the best designs on paper can fall apart if the execution doesn't follow through. And yet, despite all of that, Boston is a different city because of the Big Dig. Where the old highway once split downtown in half, there's now the Rose Kennedy Greenway, a string of parks and open space that brought life back to the street level. Traffic flows better, the waterfront is more accessible, and the scars left behind by that massive elevated road have started to heal. In the end, the Big Dig wasn't perfect, but it was bold. It pushed engineering to its limits and redefined what a city could do when it finally decided to reclaim its own space. And maybe that's the real legacy, not just the tunnels or the bridges, but the idea that even the most broken infrastructure can be reinvented, if we're willing to dig deep enough to get there. Ocean Terrace Redevelopment in Miami Beach, a project that's blending luxury, history, and sustainability into one stunning transformation. Located in the North Beach neighborhood, Ocean Terrace was once a glamorous oceanfront strip filled with Art Deco hotels and bustling shops. But over the decades, it faded. Old buildings fell into disrepair, and tourism shifted elsewhere. The area needed a reboot, and now, in 2025, it's getting exactly that. The Ocean Terrace Redevelopment Project is a $1 billion mega project designed to turn this once forgotten stretch into a modern beachfront paradise. The plan involves demolishing several aging buildings while preserving and restoring historic facades. In their place, developers are building luxury condos, a boutique hotel, retail spaces, and a revamped public beachfront park. The architectural vision is led by Arquitectonica, one of the most respected firms in Miami. The buildings will blend modern glass towers with vintage Art Deco design, creating a unique look that honors Miami's past while embracing its future. The project broke ground in 2023, and at present, construction is roaring. Workers are laying the foundations for 18-story residential buildings with underground parking garages that can handle both flooding and storm surges. Miami Beach is vulnerable to sea level rise, so developers are raising the entire site elevation using structural fill, stormwater vaults, and elevated podium decks. The buildings are being constructed with hurricane-resistant glass, reinforced concrete cores, and wind load certified materials. Heavy-duty excavators and drilling rigs are prepping the foundations, while prefabricated steel framing is delivered by barge to minimize road traffic. Crews are also using low-carbon concrete mixes to reduce emissions on site. One of the most impressive features is a 2-acre public plaza, an oceanfront park with bike lanes, shade trees, event spaces, and direct access to the beach. This green zone will be open to everyone, not just residents or hotel guests. The condos, priced in the millions, will offer floor-to-ceiling ocean views, smart home automation, green HVAC systems, and on-demand concierge services. The hotel will include a rooftop infinity pool, spa, fine dining, and luxury retail outlets. This redevelopment is expected to bring in thousands of jobs, from construction workers to hospitality staff to long-term retail operators. Once completed in 2029, this mega project will revive tourism in North Beach, pulling visitors back to an area that was once a cultural hotspot. Next up is the Keelso. The heart of the Link US Transit Corridors initiative is the task of transforming key transportation arteries in the Columbus, Ohio metropolitan region into high-capacity, multimodal corridors built for future urban growth. Unlike typical bus transit upgrades, the Link US program requires a comprehensive re-engineering of the roadway environment to support bus, rapid transit systems, pedestrian-focused infrastructure, and mixed-use urban development, all while preserving functionality for existing traffic and utility services. The first phase of physical work along a corridor typically involves relocation of utilities, both above and below ground. Electrical vaults, telecommunications ducts, gas lines, and water mains are mapped, protected, or moved to ensure that dedicated BRT lanes, new medians, and expanded sidewalks can be constructed without interference. In many cases, trenchless methods like horizontal directional drilling are employed to install new conduits beneath existing infrastructure with minimal surface disruption, particularly in dense commercial zones. Once the underground conflicts are cleared, road reconstruction begins. The new BRT lanes, often located in the center of the roadway, are built with reinforced concrete pavement sections designed for heavy axle loads and continuous operation. These lanes are separated from general traffic by raised curbs or delineators and incorporate mountable transitions at intersections to allow emergency access. Drainage patterns are revised through the addition of new catch basins, bioretention swales, and subsurface infiltration trenches, which both control runoff and improve stormwater quality. Platforms for BRT stations are constructed as raised, ADA-accessible boarding zones with tactile strips, real-time signage pylons, lighting, and weather shelters. Each station integrates with sidewalk improvements and signalized crosswalks, often requiring curb realignments and installation of new traffic signals with transit signal priority features. Median-based stations include special design considerations for pedestrian access, often requiring median refugees or fully protected intersection phases to ensure safe crossing movements. Beyond the roadway and platform work, the corridors also undergo significant landscape and urban design transformation. Utility pole removal, replacement of overhead wires with underground systems, and installation of street trees and furniture all contribute to a more pedestrian-oriented environment. Road diets are implemented in segments to reduce the number of general-purpose lanes, providing the right-of-way for wider sidewalks, cycle tracks, and designated turn lanes. These changes are reinforced with textured or colored pavement treatments at crosswalks and intersections to enhance visibility and reinforce multimodal priority. The Link US program also incorporates transit-oriented development zones adjacent to high ridership stops. Construction work in these areas involves coordination with private developers, staging of future utility corridors, and the preparation of building pads with coordinated grading and stormwater infrastructure. Each segment includes provisions for utilities and services. Garages of Texas at Lakeview in Dallas is one of those developments that only makes sense once you see it in person. A kind of private sanctuary built for people who love cars just as much as the space around them. It's not a dealership, and it's not a traditional storage facility either. It's more like a country club for car enthusiasts, designed around the idea that the garage itself can be just as important as the home. Every unit is privately owned, custom fitted, and treated like an extension of identity, turning what could have been a simple storage complex into a community built around horsepower, craftsmanship, and shared passion. The concept is deceptively simple: a gated complex of large climate-controlled garages that owners can buy, not rent, and outfit however they like. Some use them to keep vintage collections under perfect conditions. Others turn them into workshops, lounges, or even second offices. Each space starts as a blank canvas: high ceilings, polished floors, oversized roll-up doors, and a solid shell ready for personalization. From there, the customization begins. Owners add mezzanines, bars, display lighting, glass walls, or custom cabinetry, transforming raw square footage into something that feels personal and precise. The Lakeview location takes the concept a step further with its setting. It's built in a quiet pocket of North Dallas, tucked close enough to the city to be convenient, but far enough out to feel private. The surrounding area blends clean urban access with the openness of suburban layout, giving the garages the freedom to expand horizontally instead of being forced into a vertical or compressed structure. Wide drive aisles make it easy to maneuver collector cars, trailers, and lifts without stress. Everything about the layout feels like it was designed by people who actually understand what it's like to handle expensive cars. Construction quality is a major part of what makes garages of Texas stand out. The buildings use thick, insulated walls, reinforced concrete slabs, and industrial-grade fire suppression systems. Temperature and humidity control are standard, protecting cars from the brutal Dallas heat and unpredictable weather swings. Lighting is another key detail: bright, clean, and positioned for clarity, not just ambience. It's a space where someone could detail a car at midnight and still see every reflection on the paint. But what's most interesting is the culture that's grown around places like this. Even though every unit is privately owned, the complex as a whole functions like a social club. Owners get to know each other, share projects, host open houses, or simply hang out and talk shop. On weekends, the sound of engines warming up fills the air as people roll out for car meets or test drives. It's part storage, part lifestyle, a place where ownership meets community. Work on the Chicago Southside Transit Expansion starts with the mapping and alignment process, where planners determine how the new route will integrate into the existing rail network while minimizing displacement and disruption to the dense urban fabric. Surveyors conduct detailed, topographic, and structural assessments along the proposed corridor, documenting existing utilities, bridge clearances, and track geometries. Because this expansion is intended to connect neighborhoods more directly to the downtown core, special attention is given to designing stations and track alignments that fit into narrow rights of way without compromising operational speed. The first physical work often involves utility relocation. Water mains, sewer lines, and underground electrical conduits are moved to clear the way for track foundations and station structures. In many Southside neighbourhoods, these utilities are decades old, requiring replacement rather than simple relocation. Crews coordinate closely with utility companies to stage these moves so they do not disrupt service to residents and businesses. Trackbed construction is one of the core elements. For elevated sections, new steel or concrete piers are installed, often by drilling deep shafts into the ground and pouring reinforced concrete to anchor them securely. Precast guideway beams or steel girders are then set atop these supports, forming the structure on which track will be laid. For at-grade or trenched sections, subgrade preparation involves excavation, placement of a granular base, and installation of drainage systems to keep water from undermining the ballast. Stations along the expansion route are designed with high platforms for level boarding, compliant with ADA requirements. The structural work for each station typically includes reinforced concrete slabs, steel framing for the canopies, and glazing for wind and weather protection. Passenger amenities, from seating to digital arrival boards, are integrated during later fit-out phases. Where possible, station designs incorporate community-focused elements such as retail kiosks, bike storage, and public art installations. Rail systems installation proceeds in parallel. Continuous welded rail is delivered in long sections, lifted onto the guideway and clipped to concrete or timber ties. Power delivery systems are built out, whether through an overhead catenary or third rail configuration, with all cabling routed through protected conduits. Signal systems, including automatic train control and communications-based train control, are mounted and tested to allow for high-frequency, safe operations once service begins. Bridges and overpasses form an important part of the build where the expansion must cross major roads, waterways, or existing rail lines. These are often prefabricated off-site and brought in for rapid installation, reducing the need for extended road closures. In dense traffic areas, night and weekend work windows are used to minimize the impact on commuters and freight traffic. Once the physical infrastructure is in place, the testing phase begins. This includes running test trains at various speeds to verify track geometry, braking distances, and signal responsiveness. Electrical systems are load tested, station facilities are checked for operational readiness, and emergency procedures are rehearsed. Unlike traditional infrastructure projects that begin with roads and utilities, the Atlantic Spaceport Complex in Newfoundland and Labrador began with a deep analysis of coastal wind patterns, azimuth corridors, and orbital trajectories. The remote coastal site was selected specifically for its unobstructed access to polar and sun-synchronous orbits, as well as its low population density and relatively stable geology. This strategic positioning allowed for near-direct launch windows without complex flight path maneuvers, reducing both fuel requirements and orbital insertion complexity. The first stages of construction involved establishing the core operational footprint, clearing and grading vast tracts of rugged terrain while maintaining strict environmental control protocols. The subarctic climate and sensitive coastal ecosystems meant erosion control and sediment filtration systems had to be installed from the outset. This included silt fencing, drainage swales, and retention ponds strategically placed to intercept runoff from access road construction and earth-moving operations. Foundations for key facilities were drilled and anchored into the underlying bedrock, with special focus on the vertical launch platform and flame trench system. The launch pad itself was built atop a reinforced concrete slab capable of withstanding the immense thermal and vibrational loads produced during ignition. Underneath, a flame trench with diverging deflectors was cast in place using high-temperature refractory concrete designed to channel exhaust gases laterally and away from sensitive infrastructure. Adjacent to the pad, the integration facility was constructed using a pre-engineered steel frame building with overhead cranes rated for high-capacity vertical payload handling. This structure houses the vehicle assembly bay, clean rooms for payload encapsulation, and support areas for avionics checks, fueling operations, and pre-launch verification. The integration building was situated on vibration-isolated pads and includes anti-static flooring, air filtration systems, and redundant HVAC to maintain strict contamination control for orbital payloads. Fuel storage infrastructure, often a critical element of launch safety, was developed in a separate blast-buffered zone. This area includes cryogenic liquid oxygen tanks, kerosene or methane fuel silos, and purge gas systems, all with multi-layered spill containment and automated fire suppression systems. Pipelines connecting the storage yard to the launch pad were installed below grade within concrete service trenches, incorporating emergency shutoff valves and leak detection instrumentation. A specialized telemetry and tracking station was also established early in the project, featuring radar arrays, satellite uplinks, and optical tracking mounts positioned on elevated piers to ensure line of sight during all launch phases. Fiber optic data lines were buried in hardened conduits, linking this station directly to the Mission Control Center and external ground station networks. Power systems across the complex were backed up with dual redundant generators and uninterruptible power supplies to maintain continuity during critical countdown sequences. Access roads were widened and paved to accommodate heavy launch vehicle components delivered via modular transporters. Additionally, a barge landing site was constructed to facilitate oversized cargo deliveries via sea with a reinforced quay wall and mooring points integrated into the coastal rock face. There's something about a massive river crossing that just captures the imagination, especially when it doesn't involve just one bridge, but an entire network of infrastructure rising together to solve problems that have been decades in the making. The Ohio River Bridges project, connecting Louisville, Kentucky to southern Indiana, wasn't just a plan to build some new lanes of traffic. It was a full-scale re-engineering of how two states move, grow, and interact every single day. And it took more than 10 years of grinding work, tough negotiations, and a whole lot of engineering creativity to make it all happen. Instead of tackling traffic congestion with a single fix, the project took a multi-pronged approach, building not one, but two new bridges, while also overhauling one of the most complex interchanges in the region. The downtown crossing included a brand new companion bridge next to the existing Kennedy Bridge, dedicated to southbound I-65 traffic, while the older bridge was rebuilt for northbound traffic. Meanwhile, the East End crossing opened up an entirely new corridor further upstream, finally delivering on a long-promised connection that helped relieve pressure on the downtown routes and opened the door for new development outside the urban core. And then there was Spaghetti Junction, the famously tangled interchange of I-64, I-65, and I-71, which had become a nightmare for drivers and a choke point for freight, completely redesigned and rebuilt to actually work in the 21st century. But this wasn't just a road-building effort, it was a generational reshaping of the landscape, with crews moving earth, rerouting utilities, demolishing outdated structures, and threading new bridges through tight riverbanks and historic neighborhoods, all while trying to limit the impact on local businesses, homes, and daily commuters. At its peak, the project brought in thousands of workers, each playing a part in lifting steel segments into place over rushing water, pouring miles of concrete in punishing heat and cold, and operating massive cranes that swung silently through the night to avoid disrupting daytime traffic. What made the East End crossing especially challenging was the tunnel. Yes, a full-length tunnel burrowed through solid rock on the Kentucky side to preserve a historic estate and parkland, which meant engineers had to combine bridge building with tunneling expertise, groundwater management, and delicate excavation that pushed the limits of what local crews had tackled before. And while most people just see a bridge and think about the commute, the real story here is everything hiding underneath: the drainage systems, the geotechnical anchors, the seismic protections, and the realignment of roadways that all had to fit together like clockwork. It's easy to drive across one of these new spans today and take it for granted, but there's a reason the Ohio River Bridges project is still talked about as a model of regional cooperation, because it wasn't just a Kentucky project or an Indiana project. It was a shared commitment to finally solve a problem that had been kicking around for 50 years. And it's proof that even in an era of divided politics and strained budgets, big infrastructure dreams can still get built when people push hard enough and keep the long view in mind. Project in Tampa, one of the most complex and ambitious transportation mega projects underway in Florida in 2025. Located where Interstate 275 meets State Road 60, the Westshore area is one of the most vital traffic corridors in the state. It connects major destinations like the Tampa International Airport, downtown Tampa, the Westshore Business District, and nearby residential neighborhoods. For decades, this area has been a known traffic bottleneck, with frequent gridlock, crashes, and inefficient routes for commuters and freight trucks alike. The project has been in planning for more than 20 years, as transportation officials gathered data and input from the public to create a design that would actually solve the long-standing congestion issues. It finally broke ground in 2023, and in 2025, the project is hitting full throttle. The budget is projected at around $1.6 billion, funded through a combination of state, federal, and local sources. This massive investment reflects the critical importance of the interchange for the entire Tampa Bay regional economy and mobility. The redesign is nothing short of transformational. The project includes additional general use lanes, elevated flyovers, wider ramps, and dedicated express lanes to streamline traffic. There's also a strong focus on multimodal access, including dedicated bus lanes, protected pedestrian walkways, and bike-friendly routes. The construction plan is divided into phases, with the current phase in 2025 focusing on realigning key ramps and completing bridge structures. Massive steel box girders, some over 150 feet long, are being moved using multi-axle hydraulic transporters and positioned with high-capacity crane towers. Crews are using 3D modeling, ground-penetrating radar, and automated road grading systems to ensure precision and reduce costly errors. GPS-guided bulldozers, automated paving machines, and concrete slip farmers are working around the clock. Some sections of the road are being pre-assembled off-site, using modular construction techniques, speeding up the timeline while reducing noise and dust in residential zones. Below the surface, advanced stormwater management systems are being laid using tunnel boring machines. These will help prevent future flooding and keep the road safer during Florida's intense rainy seasons and hurricanes. Once completed in 2027, the Westshore Interchange will reduce travel times by up to 40%, dramatically improve safety, and allow for faster evacuation routes during emergencies. It will ease the burden on the airport, open access to growing economic hubs, and allow smoother freight movement between the port and major inland highways of Tampa. Let's travel over to Miami. Like the Puget Sound Gateway involves more than just building new roadways. It is about stitching together ports, distribution centers, industrial zones, and population centers with a network designed to withstand decades of growth and geotechnical complexity. The program hinges on completing two major corridor extensions, State Route 167 to the Port of Tacoma and State Route 509 to the Seattle-Tacoma International Airport area. These aren't simple highway extensions. They are multifaceted infrastructure systems woven through dense urban fabrics, environmentally sensitive zones, and active logistics corridors. The foundational effort began with extensive right-of-way acquisition, including dozens of industrial parcels, commercial lots, and sections of public land. Site clearing and demolition work had to be carefully sequenced to ensure active businesses and transportation flows weren't unduly disrupted. In many areas, phased demolition and temporary access roads were used to maintain traffic and construction staging efficiency. Once the sites were cleared, earthwork operations commenced with mass excavation, grading, and fill operations to establish the subgrade profiles for the new alignments. These activities often encountered unstable soils, particularly in areas near water bodies and wetlands, necessitating ground improvement methods such as stone columns, surcharge embankments, and wick drains to accelerate consolidation and avoid long-term settlement. Bridges form a central component of the Puget Sound Gateway's design, given the number of water crossings, rail corridors, and urban arterials the new routes must span. Structural systems varied by location. Some employed pre-tensioned concrete girders, while others utilized steel box girders to achieve longer spans or accommodate vertical clearance constraints. Foundations for these bridges were built using large-diameter drilled shafts socketed into glacial till or bedrock, with temporary casings and slurry techniques used where groundwater intrusion was significant. False work systems were installed with minimal encroachment on adjacent rail and road corridors, often during tight nighttime closures, coordinated months in advance. Stormwater infrastructure was a major focus throughout the corridor. Given the region's high rainfall and environmental sensitivity, advanced drainage systems were installed, including biofiltration swales, detention vaults, and oil water separators. In several segments, retrofits were made to older outfalls to meet updated stormwater discharge criteria. To further offset environmental impacts, the program incorporated significant wetland mitigation and stream restoration work. This included regrading stream beds, planting native vegetation, and installing fish-passable culverts to enhance salmon habitat connectivity. The roadways themselves were built with high modulus asphalt pavement sections capable of handling repeated heavy truckloads. Base layers were constructed using crushed aggregate wrapped in geotextile fabric to separate the subgrade from the structural layers. Intelligent transportation systems were installed throughout the new corridor sections, with fiber optic cabling laid in trench alongside the roadbeds to support variable message signs, CCTV, incident detection, and traffic management. Logistics were further complicated by the need to interface with ongoing freight rail operations and existing intermodal yards. Coordination with railroads was critical, especially during the construction of new overpasses and underpasses, where flagging operations, temporary shoring, and phased construction minimized service interruptions. Few infrastructure projects in the Northeast Corridor combined century-old obsolescence with 21st century engineering demands. Ryan Tower at the University of North Texas at Dallas is one of those buildings that captures a moment of transformation, not just for the campus, but for the whole southern side of the city. It's a tall, striking landmark that stands above the low-rolling landscape, a visual anchor for a university that's still growing into its identity. You can see it from well beyond the campus, the glass and steel catching the light in a way that makes it feel like a symbol of movement and ambition. The tower is named after the Ryan Foundation, one of the key supporters behind UNT Dallas's expansion. It's not just a classroom building, it's a statement. When the project was conceived, the goal wasn't to build another generic academic space, but to create something that gave the university a clear presence, something people could point to and recognize as the heart of campus. For a long time, UNT Dallas was spread out and modest, a commuter school without a distinct center. Ryan Tower changed that. Architecturally, it rises with a simple, modern form, straight lines, reflective surfaces, and a vertical rhythm that contrasts against the wide-open Texas sky. The materials were chosen to convey both durability and transparency. From the outside, the tower looks like a solid column of progress. From the inside, it's filled with natural light and open spaces that invite movement and interaction. The building's layout integrates offices, classrooms, and meeting areas with a focus on flexibility. Walls can be reconfigured, spaces can adapt, and the building feels alive in a way that's meant to evolve alongside the university itself. The engineering behind the structure is just as thoughtful as its appearance. The tower's frame was designed to handle wind loads that are typical for North Texas, with a reinforced core that provides stability while allowing the upper floors to stay relatively open and light. Energy efficiency was another major focus, using shaded glazing, efficient mechanical systems, and a building envelope that limits solar gain without cutting off daylight. It's the kind of detail that makes the building sustainable in the long term, both environmentally and economically. But beyond the technical aspects, Ryan Tower serves a deeper role. It gives UNT Dallas a sense of vertical identity. For years, most of the city's major academic institutions were located to the north, leaving southern Dallas underserved and often overlooked. The tower is a declaration that higher education belongs here too, that students in this part of the Metroplex deserve facilities that feel just as ambitious and inspiring as anything uptown. When you walk across campus and see the tower rising in front of you, it feels like a milestone, proof that the university has arrived. At night, the building takes on a different character. The interior lighting gives it a soft glow that can be seen from nearby highways, almost like a beacon. It's subtle, but powerful, an image of opportunity shining over a part of Dallas that's often hungry for it. Let's move over to Kuala Lumpur, Malaysia, where the recently completed Merdeka 118 stands tall at 678.9 meters. This architectural marvel is the second tallest building in the world, just behind Burj Khalifa in Dubai and the tallest in Southeast Asia. Formerly known as Menara Warisan Merdeka and PNB 118, the name of the tower, Merdeka, meaning independence in Malay, reflects the proud history of Malaysia. It stands firm, standing the iconic Stadium Merdeka, where the country's independence was declared in 1957. Construction began in 2014 and officially concluded in 2023, with the tower inaugurated in January 2024. The project, funded by Permudalan National Berhad, a government-owned investment firm, came with a hefty price tag of $1.5 billion. Despite public criticism regarding its cost, the government emphasized its role in generating economic opportunities and elevating the global presence of Malaysia. Designed by Fender Katsalides architects, the structure of Merdeka 118 is inspired by the outstretched hand gesture of the first Malaysian Prime Minister, Tunku Abdul Rahman, as he proclaimed independence. The diamond-shaped glass facade symbolizes the country's diversity, consisting of 18,144 panels and 114,000 square meters of glass. The tower houses 118 floors, including premium office spaces, a luxury Park Hyatt hotel, and the highest observation deck in Southeast Asia, offering panoramic views of Kuala Lumpur. A sprawling 118 mall, residential units, and a business center add to its multifunctional appeal. It also features 8.4 kilometers of LED lighting, illuminating the Kuala Lumpur skyline at night. The construction of Merdeka 118, a super tall skyscraper, involved a range of advanced techniques to overcome the challenges of its height and complex design. The slip-forming technique was used to build the core of the tower. This technique involves continuously pouring concrete into a moving formwork, allowing the core to rise steadily. Certain sections of the tower, particularly the spire or facade elements, were prefabricated off-site and then assembled on-site. This modular approach speeds up construction and improves quality control. The facade of Merdeka 118 likely utilizes a sophisticated cladding system, probably a combination of glass panels and metal components. These systems are designed for weatherproofing, insulation, and aesthetics. Let's discuss the tallest mega project. In the case of the Coastal Virginia Offshore Wind Project, the entire effort hinges on the careful coordination of marine construction in open ocean conditions. which demands a completely different approach than land-based renewable energy developments. The process begins long before any steel touches the water with an exhaustive geotechnical survey of the seabed. Crews deploy specialized survey vessels equipped with multi-beam sonar, sub-bottom profilers, and cone penetration testing equipment to map the subsurface layers in fine detail. This information dictates the exact placement and design of the turbine foundations, as the Atlantic sandy sediments can vary greatly in density and composition over relatively short distances. Once the optimal positions are confirmed, the installation phase for the foundations begins. Jack-up installation vessels, capable of lifting themselves out of the water on massive legs for stability, are mobilized to the site. Each turbine foundation, typically a monopile in this particular project scale, is fabricated onshore, transported by barge, and then driven deep into the seabed using hydraulic impact hammers. To prevent scouring around these foundations from constant wave and current action, a protective layer of rock armor is placed at the base, delivered by fall pipe vessels that can accurately drop stone in rough seas. Following the establishment of foundations, transition pieces are installed. These are cylindrical structures fitted over the top of the monopiles, designed to provide a precise connection interface for the turbine towers. Inside these transition pieces, workers fit ladders, cable hang-offs, and landing platforms for future maintenance access. All bolted connections are pre-tensioned to exact specifications, and every weld is inspected both visually and with non-destructive testing to ensure long-term durability in the harsh marine environment. Parallel to the structural work, cable laying operations take place. High voltage export cables, manufactured in continuous lengths, are loaded onto specialized cable laying vessels equipped with large turntables. From the offshore site to the onshore landing point, the cable is carefully placed into pre-dredged trenches and then buried using either jetting or ploughing systems to protect it from anchors and fishing gear. Near shore, horizontal directional drilling is used to pull the cable through to a land-based transition station without disturbing the beach or nearshore ecosystem. The turbine assembly process is one of the most visually striking parts of the project. Tower sections, nacelles, and rotor blades are transported offshore and installed in a carefully choreographed sequence. Tower sections are lifted and bolted together first, followed by the placement of the nacelle, the housing for the generator and gearbox, and finally, the massive blades, each of which can be well over 100 meters in length. Given the limited weather windows for safe lifts, every component's arrival and installation is timed to the hour. Back on shore, the grid connection infrastructure is constructed. This includes the installation of transformers, switchgear, and protection systems to integrate the offshore generation into the regional power network. Once testing and commissioning are complete, the wind farm begins full operation, delivering clean energy while being monitored from an onshore control center that can track turbine performance, detect anomalies, and even adjust blade pitch remotely to maximize efficiency and minimize wear. What set the Darlington Small Modular Reactor project apart from the beginning was its use of a fully licensed, pre-developed nuclear site, something exceedingly rare in the nuclear industry. The Darlington Nuclear Generating Station in Ontario had long maintained a site preparation license for future expansion, which streamlined early regulatory processes for the Small Modular Reactor, or SMR. This advantage allowed project teams to initiate earthworks and enabling infrastructure much earlier than would typically be possible for a new nuclear build. Initial site development began with large-scale excavation to accommodate the reactor island, turbine structures, and support facilities. Rock blasting and removal were required to reach the design depth for seismic and flood protection. The site lies near Lake Ontario, so hydrological modelling informed the grading strategy and stormwater detention systems. Extensive cut and fill balancing was undertaken to minimise material export and optimise the site's profile for future service roads and vehicle access. Subsurface characterization was essential for the foundation design of the SMR. Geotechnical boreholes and core sampling provided detailed profiles of the limestone bedrock and glacial till overlay. Once the excavation reached bedrock, foundation work began with rock anchors, concrete mud slabs, and waterproofing layers. The nuclear island foundation required a heavily reinforced concrete mat slab designed to distribute high concentrated loads from the reactor vessel and containment structures. The SMR selected for Darlington is a pressurized water reactor with integrated steam generation and passive safety features. The reactor building is being constructed using modular components prefabricated off-site, including sections of the containment structure, equipment modules, and piping skids. These modules are shipped by rail or specialized trucks and assembled using heavy lift cranes on engineered laydown pads adjacent to the foundation. The modular approach dramatically reduces on-site labor requirements and improves quality control by shifting fabrication into controlled environments. Containment and auxiliary buildings use thick reinforced concrete walls with embedded steel liners and seismic isolation joints. Key safety systems, such as the passive heat removal system, emergency core cooling, and spent fuel cooling, are embedded in compact configurations to allow for the SMR's reduced footprint. Embedded conduits, grounding grids, and shielded penetration sleeves are installed in formwork before concrete is poured, ensuring precise alignment and shielding performance once complete. The turbine island, located adjacent to the reactor building, is built on deep foundations and houses the generator, condenser, feed water heaters, and auxiliary equipment. Although the power output of an SMR is smaller than traditional nuclear units, the turbine equipment must still meet exacting standards for steam quality, thermal cycle efficiency, and vibration performance. Heat rejection is handled through mechanical draft cooling towers with high-efficiency fans and drift eliminators, positioned to avoid fogging and icing in prevailing wind conditions. Grid connection infrastructure includes switch yards, step-up transformers, and control systems, all housed in electromagnetically shielded buildings. A centralized control facility oversees both reactor and balance of plant systems, using digital instrumentation and control platforms with redundant safety class architectures. Sometimes the only way to fix a traffic nightmare is to dig right through it, and that's exactly what's happening under the waters of the Chesapeake Bay with the Hampton Roads Bridge Tunnel Expansion, a project so massive and technically complex that it feels more like a feat of underwater surgery than roadwork. This isn't just about adding a few extra lanes or patching up a tired old road. This is about carving out a brand new tunnel system, right alongside the existing ones, and doing it all while millions of drivers still rely on this corridor every year to get in and out of Norfolk, Virginia Beach, and the rest of the Tidewater region. What's wild is that for decades, the original tunnels were just barely holding the line. 2 narrow lanes in each direction, squeezed by growing demand, constant military traffic, and a metro area that kept expanding while the bottleneck never changed. So now, instead of playing catch-up every few years, they're going big, with 2 new bored tunnels being drilled straight through the seabed, side by side, each wide enough to carry full interstate traffic and built using one of the largest tunnel boring machines ever deployed in North America. The machine itself is a behemoth, longer than a football field, with a rotating cutter head that chews through clay, sand, and bedrock like it's slicing through cake, pushing forward inch by inch while simultaneously laying down precast concrete segments to form the lining of the tunnel behind it. But tunneling is only part of the story, because above ground, the entire stretch of I-64 across the bridge tunnel complex is being widened as well, with new bridges rising from the water, traffic patterns being realigned, and interchanges being redesigned to finally eliminate the backups that have been part of daily life in this area for as long as anyone can remember. The work zones are intense, with crews working day and night on floating platforms, barges, and cranes, all surrounded by a working waterway filled with cargo ships, Navy vessels, and pleasure boats that can't afford to be delayed. Coordinating all of that without shutting down the region's economy or disrupting naval operations is a balancing act that requires military-grade logistics and relentless planning. And then there's the weather, because on top of the technical challenges, this is a region constantly exposed to hurricanes, tidal surges, and high winds, which means every element of this project, from the tunnel's waterproofing systems to the bridge expansion joints, has to be built with extreme resilience in mind. There's no room for shortcuts out here, not when lives, livelihoods, and national defense all depend on this corridor staying open. In the end, the Hampton Roads Bridge Tunnel expansion isn't just a fix for traffic. It's a massive leap forward in how this region connects with itself and the world beyond. Once it's finished, the flow of people, goods, and military readiness will all be transformed, not by one big moment, but by years of hard digging, steel lifting, and non-stop determination. And if you've ever sat in that bumper-to-bumper line, staring out at the water, wondering why it's taking so long to move, well, this is the answer. They're not just building lanes, they're building a future. Stadium renovation. A project so ambitious, it could redefine how sports stadiums are built in America. Located in downtown Jacksonville, Everbank Stadium, formerly known as TIAA Bank Field, has been home to the Jacksonville Jaguars since 1995. But in recent years, fans, players, and officials all agreed it was time for something new. That's why the Jaguars and the city of Jacksonville teamed up to launch a $1.4 billion stadium transformation. In 2025, the construction is in full swing and turning heads. The project is being called the Stadium of the Future, and when you look at the details, it's easy to see why. The idea was first announced in 2022, with renderings that stunned the sports world. After negotiations between city officials and the Jaguars organization, construction began in late 2023. Now, in 2025, the stadium is a full-blown construction zone, surrounded by cranes, scaffolding, and non-stop activity. The new design includes a futuristic canopy roof made with a lightweight, transparent material that shields fans from rain and sun without blocking natural light. It will cover over 90% of the seating area and reduce the on-field temperature by nearly 20 degrees. The stadium will also feature outdoor terraces, expanded concourses, 360-degree views, and 5 G-ready smart infrastructure. Everything, from the bathrooms to the concession stands, is being rebuilt with comfort, speed, and technology in mind. The renovation plan includes wider seats, more premium lounges, and upgraded ADA access. There will also be dedicated spaces for community events, youth sports, and even concerts and esports tournaments. Fans will enjoy wider seats, more legroom, and better sightlines from all angles. Underneath the surface, engineers are reinforcing the existing foundation using micropile drilling, ensuring it can support the new steel roof and upper decks. For the structure itself, modular steel trusses are being hoisted into place using crawler cranes that can lift up to 500 tons at once. Construction teams are also working on upgrading all electrical and water systems. New fiber optic lines are being installed for high-speed internet, instant replay features, and augmented reality apps fans can use during the game. It's part of a bigger push to make this a smart stadium. The materials are cutting edge. The canopy will feature lightweight tensile fabric, allowing airflow while keeping out heat. Seating areas are being built with UV-resistant, recyclable materials. The project also includes solar panel arrays to offset the power use of the stadium. By the time the project wraps up, expected in 2028, Jacksonville will have a stadium to support year-round events, from concerts to college games to global tournaments. Next up, we have to talk about the Freedom Park Scale of Sound Transit 3 demands a construction strategy that spans decades. integrates multiple jurisdictions and aligns civil, systems, and structural engineering disciplines across a vast and varied geography. This voter-approved expansion of regional transit infrastructure in the Puget Sound area includes new light rail lines, commuter rail improvements, and bus rapid transit corridors, all designed to accommodate a rapidly growing metropolitan population and its shifting transportation needs. At the core of Sound Transit, 3's physical execution is the construction of hundreds of miles of new guideway, some elevated, some underground, and others at grade, depending on topographic and urban constraints. In urban centers like Seattle, tunneling is a dominant component, requiring the use of tunnel boring machines launched from deep access shafts. These shafts are constructed using secant, pile, or diaphragm wall methods, followed by excavation and concrete base slabs to support TBM assembly. As each tunnel progresses, precast segmental lining is installed immediately behind the cutter head, and grout is injected into the annular space to stabilize the ground and ensure watertightness. In suburban and exurban areas, elevated guideways are more cost-effective and less disruptive. These are constructed using precast segmental box girders, supported on piers founded on drilled shafts or driven piles. Span-by-span erection methods, including balanced cantilever or launching gantries, are used to minimize construction footprint and expedite the schedule. Each pier is precision aligned to maintain track geometry, and expansion joints are incorporated to account for thermal movement and seismic activity, critical factors in the seismically active Pacific Northwest. At-grade sections, while more straightforward to build, require extensive utility coordination, signal integration, and roadway modifications. Track slab construction includes sub-ballast, geotextile membranes, and continuous welded rail affixed with elastomeric fasteners for noise and vibration control. Crossings at intersections include embedded track panels and are integrated with intelligent transportation systems for preemption and safety. Station construction across the Sound Transit 3 network varies by location and function. Urban stations often require deep excavation and support of excavation systems such as soldier piles and lagging or secant piles. Platform construction includes structural slabs, canopy systems, tactile guidance elements, vertical circulation components such as elevators and escalators, and integrated fare control areas. Suburban and elevated stations are typically built on structural steel or precast concrete platforms, allowing for faster modular assembly. Mechanical and electrical systems, ventilation, fire suppression, power distribution, and communications are standardized across the network but require bespoke design at each site to accommodate geography and usage. Overhead contact systems for power delivery are strung on catenary poles or integrated into tunnel soffits using rigid conductor bars. Signaling systems use automatic train control with centralized monitoring and dispatch centers, all fiber connected through continuous cabling installed alongside track or in dedicated utility conduits. The Sound Transit 3 program is being delivered in carefully sequenced phases, with each segment undergoing planning, environmental clearance, design, procurement, and construction on overlapping timelines. Coordination with local utilities, city planning departments, and environmental agencies is ongoing throughout the life cycle. Simultaneously, worksite safety, noise control, and public interface management are embedded into each contract package to minimize community disruption. Transform Toyota Music Factory in Irving is one of those places that feels like it was built for motion, for people coming and going, for crowds shifting from dinner to a show, for music spilling out onto patios on a warm Texas night. It sits right in the heart of Las Colinas, a district that's long been known for offices and corporate campuses, and it brings something completely different to the area: a pulse. The whole complex is designed around entertainment, food, and connection, creating a kind of urban village where everything happens in one spot. At its core is the Pavilion, the centerpiece venue that gives Toyota Music Factory its identity. It's not just an arena, it's an adaptable space that can transform depending on the size of the event. On some nights, it functions as an intimate indoor theatre for a few thousand fans, and on others, the back wall opens up to reveal a sprawling outdoor amphitheatre that can hold a crowd big enough to fill a small stadium. The engineering that makes that transformation possible is remarkable. Massive retractable panels, acoustic treatments that shift with the space, and lighting systems that adjust seamlessly from concert to open-air festival mode. Surrounding the pavilion is a grid of restaurants, bars, and smaller performance spaces that create a true district feel. The developers didn't just drop in a venue, they built an ecosystem around it. The pedestrian plazas are lined with wide shaded walkways, and there's always a hum of activity, whether it's people pre-gaming before a show or lingering afterward. The outdoor spaces are what really sell it though. Fountains, open lawns, and string-lit patios that feel casual but carefully planned. You can tell the goal was to make it just as enjoyable on a quiet Tuesday night as on a packed concert weekend. From an infrastructure standpoint, the Music Factory was a complex build. The site sits near major roadways and DFW airport flight paths, so engineers had to work around noise mitigation, traffic flow, and parking capacity for thousands of visitors. The parking structures were integrated into the design instead of pushed off to the edges, with direct pedestrian connections leading right into the heart of the plaza. The entire development sits on a mix of concrete and landscape decks, with stormwater systems built underneath to manage runoff from both the buildings and the paved areas. It's a good example of how entertainment architecture now has to balance spectacle with practicality. The acoustics and stage engineering inside the pavilion are worth mentioning too. Every panel, every curve was shaped to deliver sound that feels full and even no matter where you're sitting. Touring acts praise it for that reason. It's built for the modern touring circuit, flexible enough to host everything from pop concerts to stand-up comedy to orchestral performances without losing quality. But maybe the most interesting part of Toyota Music Factory is how it reshaped perception. For years, Las Colinas was known for its daytime crowd, business suits, office parks, conference centers. This project turned it into a place that stays alive after sunset. It gave the area a new rhythm and helped redefine Irving as more than just a stop between Dallas and Fort Worth. For the Rio Grande LNG Train Expansion, work begins with an expansion plan that integrates seamlessly into the existing LNG facility's footprint while preserving safe operational distances between high-pressure equipment, storage tanks, and process lines. Civil engineering teams start by clearing and grading the designated construction pad, ensuring that the soil can bear the immense weight of cryogenic process modules and auxiliary systems. In this Gulf Coast environment, deep foundation piling is often required, with driven steel or precast concrete piles installed to reach stable strata below layers of soft, saturated soil. Once the ground improvements are complete, crews set out the anchor bolt patterns for the heavy process equipment foundations. Each foundation is a precisely engineered, reinforced concrete block designed to resist not just static weight, but also dynamic forces from machinery vibrations. Underground utilities, including cryogenic piping corridors, electrical conduits, and stormwater drainage, are laid early to avoid future excavation near high-risk areas. The core of Train 4's expansion revolves around its liquefaction process modules. These modules, typically prefabricated in large sections off-site, arrive via heavy lift transporters and are set in place using high-capacity crawler cranes. The arrangement includes gas pre-treatment units to remove CO2, H2S, and water vapor, followed by the main cryogenic heat exchangers and refrigeration compressor trains. These components operate under extremely low temperatures, so all associated piping is fitted with multi-layer insulation systems, vapor barriers, and stainless steel or aluminum cladding to prevent ice buildup and energy losses. Interconnection with the existing plant requires tie-ins to common utilities such as cooling water, nitrogen, instrument air, and flare systems. These tie-ins are executed during carefully scheduled outages or low load periods to minimize disruption to ongoing LNG production. High-pressure piping spools are hydro-tested to verify integrity before being connected, and every weld undergoes radiographic inspection for quality assurance. Electrical and control systems for Train 4 are integrated into the plant's distributed control system. Cable trays are installed on multi-tier racks, and miles of control and power cabling are pulled, terminated, and tested. Motor control centers, variable frequency drives for compressor motors, and backup generator systems are positioned within blast-resistant buildings to ensure operational continuity in case of an incident. Safety instrumented systems, including emergency shutdown valves, fire and gas detection sensors, and deluge systems, are calibrated and tested extensively before commissioning. Storage and loading infrastructure is evaluated to confirm that the expanded capacity can be accommodated. This may involve adding new LNG storage tanks or upgrading loading arms and pumps at the marine berth. LNG storage tanks are constructed with inner nickel steel shells and outer concrete shells, with polite insulation filling the annular space to maintain cryogenic temperatures. Instead of beginning with tracks or vehicles, the Green Line LRT in Calgary was initiated through a comprehensive utility relocation and ground improvement program. Before any vertical construction or tunneling could proceed, dozens of kilometers of buried infrastructure, stormwater pipes, sanitary lines, electrical ducts, and fiber optics had to be identified, protected, rerouted, or upgraded. In several locations, these utilities intersected at dense nodes beneath arterial roads and future station sites, requiring meticulous planning and trenchless methods such as micro-tunneling and pipe jacking to avoid service disruptions in heavily trafficked areas. Once the utility clearance phase was sufficiently advanced, work progressed into the early stages of civil construction. The Green Line, spanning a mix of underground, elevated, and surface-level segments, called for an array of structural systems. In the downtown core and Beltline areas, tunnel construction formed a significant portion of the work. This involved sequential excavation methods with the use of temporary steel ribs, shotcrete, and soil anchors to support the advancing tunnel crown in low overburden areas. Where ground conditions allowed, pressurized face tunnel boring machines were scheduled to be deployed, operating in glacial tills and mixed soils with varying water tables. Tunnel station boxes, such as those planned beneath 2 Street SW and Centre Street, demanded deep excavations in urban zones flanked by high-rise foundations. For these station caverns, diaphragm walls or secant piles were used to form rigid shoring systems, and ground freezing techniques were planned for groundwater control and soil stabilization in permeable layers. Real-time instrumentation was installed throughout excavation zones to monitor settlement, vibration, and deformation, with automated feedback loops to adjust construction parameters as needed. Outside the core, where the line transitions to surface and elevated alignments, earthworks and structural pier foundations dominated. Embankments were constructed using engineered fill, layered and compacted to specific densities, while concrete piers for elevated guideways were drilled into bedrock or dense till strata. Precast guideway segments were manufactured off-site and transported to staging areas, then lifted into place using mobile cranes and segment lifters, particularly for long spans over roadways and rail corridors. The vehicle maintenance and storage facility, a critical component located in the Shepherd area, was built early in the project timeline to serve both staging and future operations. It included track work for vehicle testing, inspection pits, overhead catenary systems, control centers, and heavy-duty paving designed to handle the specialized weight and turning radii of light rail vehicles. Concurrently, track installation began using both embedded slab track in urban areas and ballasted track in outlying zones, with special attention paid to noise and vibration attenuation through resilient rail pads and floating slab systems. The Green Line stations varied significantly in typology, from fully underground platforms to elevated and at-grade stops with canopies and weather-protected waiting areas. All station designs incorporated accessibility features, tactile warning strips, and provisions for future system expansion. Pedestrian connections, public realm integration, and intermodal transfers were key design drivers, particularly where the line intersected with bus corridors or major arterial roads. You know, it's hard to even recognize parts of JFK right now if you haven't been in a while, because the place is changing faster than most people realize. And what's unfolding out there isn't just another round of airport renovations or cosmetic updates. It's one of the most ambitious and complex aviation overhauls ever attempted in the United States, with over $19 billion being poured into a complete reimagining of how millions of people move through one of the busiest air corridors on the planet. And what's really wild is that all of this is happening while planes are still landing, passengers are still moving, and operations are continuing 24 hours a day. At the center of this transformation is the creation of an entirely new Terminal 1, which is so big and so advanced that it's being built in phases like a city unto itself. And when it's finally done, it's going to be over 2 million square feet of sleek glass, steel, and high-tech systems designed to move international passengers faster, smoother, and with far more comfort than anything JFK has ever offered. And just to put that in perspective, that's about the size of 35 football fields stitched together, all meant to replace the aging Terminals 1 and 2 and part of Terminal 3, which were never really designed for the kind of traffic and pressure they're under today. But what's really impressive isn't just the scale. It's the way this entire redevelopment has been planned like a master puzzle, with Terminal 4 getting expanded for Delta to consolidate its operations, Terminal 6 being brought back from the grave and connected directly to JetBlue's Terminal 5 so passengers can finally have a seamless experience transferring between domestic and international flights, and the air train being upgraded to keep pace with the tidal wave of future demand. And when you think about how all of that has to be coordinated across separate contractors, airlines, funding sources, and public agencies, all while navigating insane logistical challenges like rerouting roadways and maintaining security zones, it becomes clear just how much engineering muscle and human coordination is being flexed behind the scenes. And of course, none of this is simple, because every time a new section opens or an old one shuts down, there's a ripple effect across the entire system, which means that construction crews, air traffic controllers, baggage handlers, and security personnel are all having to work around each other in this constantly shifting dance where timing is everything, and the margin for error is practically zero, because even a small delay in one part of the airport can throw off dozens of flights, hundreds of workers, and thousands of passengers, which is why this project is just as much about logistics and systems thinking as it is about steel and concrete. What's happening at JFK right now is nothing short of a reinvention, a complete teardown and rebuild of the way this airport functions from the ground up. And when it's all finished, the hope is that JFK will no longer be the overcrowded, outdated, chaotic experience that travelers love to complain about, but instead a world-class hub that reflects the scale and ambition of the city it serves. So the next time someone asks you why there are so many construction walls and detours at JFK, you can tell them it's because they're building the future, one terminal at a time. Capacity Improvement Project. If you thought the Westshore Interchange was big, this one might just surprise you. Interstate 275 is the main highway of the famous Tampa Bay, running straight through the city. This $580 million mega project is about widening, modernizing, and future-proofing one of the most congested freeway stretches of Florida. It targets the corridor from north of the downtown interchange to Bears Avenue, a section that regularly sees bumper-to-bumper traffic. The project is a direct response to the rapid growth of the region, with Tampa and nearby areas adding over 100,000 new residents in recent years. More people means more traffic and more pressure on aging infrastructure. The project officially launched in late 2022, and in 2025, construction is fully underway. Crews are focused on adding one new general use lane in each direction, upgrading interchanges, and installing intelligent transportation systems to improve traffic flow. The project includes widened shoulders, noise-reducing walls, stormwater upgrades, and LED roadway lighting. There's also a special focus on safety with enhanced guardrails, crash cushions, and barrier walls being installed. Construction is happening in phases to avoid full shutdowns and keep traffic moving. Day and night shifts are being used, along with lane management strategies that help limit closures during peak hours. To speed things up, crews are using automated grading machines, paver finishers, and laser-guided concrete cutters. For structural work, precast box culverts and modular retaining walls are being dropped into place using hydraulic cranes. Real-time sensors continuously track pavement compaction. Drones monitor construction progress and detect any errors. BIM software is used for scheduling, clash detection, and team coordination. What makes this project especially modern is the use of adaptive traffic control systems. These systems will allow traffic lights and highway signs to respond automatically to real-time conditions, accidents, or weather problems, helping drivers make faster, safer decisions. Diverse fiber optic cables are being embedded along the roadbed. These will support future autonomous vehicle technology and allow faster emergency response communication. The project also includes multi-use paths and pedestrian bridges, making it safer for those who walk or bike in the area. Once complete, targeted for 2026, the I-275 expansion will cut travel delays, increase road capacity, and reduce accident-related closures. It's a critical piece of the puzzle for the vision of Florida to build and maintain a seamless, high-tech highway network. But just wait until you hear about a new light rail system in a rapidly urbanizing environment like Austin, Texas, demands a tightly orchestrated series of construction phases, each calibrated to balance public disruption, environmental stewardship, and long-term transit capacity. Project Connect Light Rail, central to the city's broader transportation strategy, represents a blend of civil infrastructure, systems integration, and urban design. Its construction is not only about laying tracks, but also about reconfiguring the city's mobility framework from the subgrade utility level all the way up to station canopies. Initial phases of the work required a thorough utility mapping and relocation campaign, especially in downtown Austin, where decades of layered infrastructure, water mains, electric duct banks, storm drains, and fiber optic lines occupied the corridors targeted for track alignment. Crews deployed vacuum excavation techniques and ground-penetrating radar to verify as-built conditions, followed by jack and bore and open-cut trenching to shift essential services out of the right-of-way. This preliminary but crucial step enabled the mainline guideway construction to proceed without repeated conflicts or delays. As alignments were cleared, track bed preparation commenced with excavation, soil stabilization, and sub-ballast installation. In sections where the light rail operates at grade, the track slab was constructed using reinforced concrete with embedded direct fixation fasteners, allowing for precise gauge control and long-term durability under repeated thermal and dynamic stresses. In downtown segments, where aesthetic and spatial considerations dominate, tracks were encased in special surface treatments, integral colored concrete, brick pavers, or textured asphalt, to blend seamlessly with pedestrian zones while maintaining proper clearance envelopes and safety delineations. Where the alignment transitions onto elevated guideways or bridges, segmental box girder construction was utilized. Precast segments were manufactured off-site in controlled environments, then transported to staging areas and erected using launching gantries or crawler cranes, depending on site access constraints. These structures had to be designed for both dynamic train loading and lateral wind forces, while also accommodating future utilities and maintenance walkways. Each segment connection used post-tensioning tendons and epoxy joints to ensure monolithic performance and structural integrity. Stations themselves were constructed with a modular approach. Precast platforms, canopy structures, and mechanical cores delivered to site and installed with minimal wet trades. ADA compliance, passenger safety, and urban connectivity guided the architectural layout, with integrated drainage systems, tactile strips, wayfinding systems, and lighting installed as part of the core station package. At intermodal hubs, construction was further complicated by the need to synchronize with bus bays, parking structures, and bike ped infrastructure. Power and signaling installation occurred in parallel with guideway and station build-out. Overhead catenary systems were supported by steel poles anchored into micro-pile or spread footing foundations, with tensioning devices calibrated for thermal expansion ranges. Communications-based train control systems were integrated along the alignment with underground fiber routes, trackside equipment cabinets, and centralized operations centers ensuring constant feedback and real-time train location monitoring. Breaking ground on a regional freight mobility program, the Margaret McDermott Bridge is one of those projects that shows just how much Dallas loves to think big, even when the road to getting there isn't smooth. Spanning the Trinity River, it was built as part of the massive Horseshoe Project, a sweeping reconstruction of the downtown Mixmaster Interchange that handles some of the heaviest traffic in Texas. On paper, it was meant to be both an engineering upgrade and a visual statement, a combination of strength and sculpture that would redefine how people entered the city. The bridge itself carries Interstate 30, connecting the west side of Dallas to the urban core. It replaced an older, worn-out structure that had been straining under decades of use, and engineers saw a chance to do more than just rebuild. They wanted to create something iconic. The design was centered around two soaring steel arches, pure white against the skyline, curving gracefully over the river with cables dropping down to support the deck below. It was intended to be part of Santiago Calatrava's broader vision for the Trinity River Corridor, linking up visually with the earlier Margaret Hunt Hill Bridge just to the north. But the McDermott Bridge wasn't just about looks, it was tied directly into the Horseshoe Project, a huge effort led by the Texas Department of Transportation to completely overhaul the tangled web of highways looping around downtown. The interchange between I-30 and I-35E had long been a nightmare. Tight ramps, short mergers, constant bottlenecks, and the project aimed to rebuild it from the ground up. Over several years, crews restructured bridges, realigned lanes, and rebuilt overpasses, all while keeping traffic moving through one of the busiest corridors in the state. The Trinity River itself adds another layer to the story. For decades, Dallas treated it more like a barrier than an asset, but projects like this have slowly started to change that. The McDermott Bridge was supposed to help turn the riverfront into something people could actually use and enjoy. It was designed with pedestrian and bike paths built into its structure, connecting to future trails and parkland along the floodplain. The idea was to make it not just a piece of infrastructure, but a public space, an everyday link between neighborhoods on both sides of the river. Of course, the road from a concept to completion wasn't perfect. The project faced cost overruns, delays, and some serious engineering challenges, particularly with the tension cables and wind performance of the pedestrian components. The bridge opened for vehicle traffic first, while the pedestrian sections took much longer to become safe and usable. But even with its complications, it stands today as one of the most recognizable features along I-30, its twin arches rising over the Trinity like giant gateways to the city. Together, The Margaret McDermott Bridge and the Horseshoe Project reshaped how people move through Dallas. The rebuilt highways relieved a notorious choke point. The bridge gave the skyline another landmark, and the Trinity Corridor gained another piece of its long-term transformation. It's a reminder that progress in a city this size rarely happens cleanly. It comes through persistence, revision, and a willingness to keep pushing until something lasting takes shape. Jinping Eye Dam in China, the tallest arch dam in the world, standing at 305 meters, located in the rugged mountains of Sichuan province. This colossal structure utilizes the mighty flow of the Yalong River to generate hydroelectric energy for millions. The idea of harnessing the hydropower potential of the Jinping Bend has been in the works since the 1960s. The unique geography of the area presented an incredible opportunity. While the river loops around the Jinping Mountains for 100, constructing the Jinping Eye Dam was no easy feat. Engineers had to carve through rugged mountains to create deep diversion tunnels, some extending over 17 kilometers, among the longest in the world. The regional geological instability posed additional risks, including the occurrence of reservoir-induced seismicity. In 2013, several small earthquakes were recorded during the impoundment phase of the reservoir, with magnitudes ranging from 3.9 to 4.58 on the Richter scale. To address these risks, engineers implemented advanced monitoring systems and reinforced key structural elements to ensure long-term stability. The foundations of the dam were meticulously anchored into the bedrock to withstand the immense water pressure and seismic activity. But next up, we have to talk about the iconic. For a highway project like the Music City Loop in Nashville, the starting point is always the land acquisition and right-of-way preparation, which determines how the alignment will weave through existing terrain, neighborhoods, and commercial zones. Survey teams first establish precise control points along the proposed corridor, mapping every contour, property boundary, and existing utility line. This is crucial because a loop system must integrate with multiple interstate connections and arterial roads, requiring interchange designs that balance traffic flow with structural feasibility. Earthwork operations follow swiftly. Large bulldozers and excavators strip the topsoil and begin the cut and fill process, where high ground is lowered and low ground is raised to create the desired grade. In areas with soft clay or alluvial deposits, engineers implement soil stabilization techniques such as lime or cement treatment to improve bearing capacity. Where the loop crosses floodplains near river channels, elevated embankments or viaduct structures are introduced to maintain year-round access and protect against inundation. Bridges and overpasses become major focal points in a project of this scale. Concrete girder bridges are common, with precast elements fabricated at a yard and trucked to the site. Each girder is lifted into place with cranes, set on reinforced concrete piers and abutments that are themselves anchored into drilled shafts or driven piles. The deck is then formed, poured, and cured, after which barriers, lighting, and expansion joints are installed. Interchanges may require multi-level flyovers, demanding complex formwork systems and staged construction to maintain partial traffic movement during the build. Pavement construction is handled in a phased manner. The prepared subgrade receives a layer of granular base, compacted to exact density targets, followed by an asphalt binder course, or, in high-load sections, a continuously reinforced concrete pavement. For the loop's heaviest traffic zones, particularly where freight corridors converge, thicker pavement designs are used to accommodate decades of truck traffic without structural failure. Stringent quality control testing on material gradation, asphalt mix temperature, and concrete slump is conducted daily. Drainage infrastructure runs in parallel with the roadbed work. Culverts, storm sewers, and retention basins are placed to control runoff. And in urban approaches, curb and gutter systems with underground piping route stormwater intermunicipal systems. Because Nashville's topography includes rolling hills and sudden elevation changes, slope stability measures such as retaining walls, riprap armoring, and geotextile reinforcements are integrated into the design. Signage, guardrails, lighting, and intelligent transportation systems form the final operational layer. The ITS components, including traffic cameras, variable message boards, and ramp metering signals, are wired into a centralized control hub that can monitor congestion, detect incidents, and adjust lane use or ramp flow in real time. Noise barriers are installed where the loop borders residential areas, designed with absorptive panels to reduce highway sound levels. Throughout the construction process, coordination with utility companies ensures the relocation of water mains, gas lines, fiber optic cables, and electrical transmission lines without halting progress. Staging and sequencing are meticulously planned so that bridge crews, paving crews, and utility contractors can work in overlapping zones without interfering with one another. Rather than beginning with earthwork or bridge segments, the Patullo Bridge Replacement Project was first shaped by how it had to coexist with the structure it was replacing. The original bridge, a narrow steel truss span opened in 1937, needed to remain operational throughout construction. This imposed significant constraints on staging, alignment, and work zone safety, requiring meticulous sequencing and traffic management planning from the outset. The new bridge was aligned slightly upstream to minimize interference, allowing major works to proceed in parallel with live traffic. The new crossing was designed as a modern, 4-lane, cable-stayed bridge with provisions for eventual expansion to 6 lanes. Foundation construction began with installation of deep drilled shafts and large diameter caissons sunk into the riverbed. These elements, some exceeding 2 meters in diameter and extending dozens of meters into the underlying strata, formed the base of the bridge's main tower piers. Working in the Fraser River's dynamic flow regime meant cofferdams and silt curtains had to be used extensively to manage turbidity, prevent sediment transport, and protect aquatic habitat during pile installation and excavation. Above the waterline, the main towers were cast incrementally using climbing formwork systems. Each tower leg was built in a series of lifts, reinforced with dense rebar cages and post-tensioned anchors to resist the immense tension forces from the stay cables. These vertical elements were built with ultra-high performance concrete mixes tailored for marine exposure, freeze-thaw durability, and long-term strength gain. Cable installation followed a balanced cantilever method, where stay cables were added symmetrically from each tower to support segments of the bridge deck as they were assembled. The deck segments themselves were prefabricated off-site and barged to the location, then lifted into position using floating cranes and strand jacks mounted on temporary erection towers. As each segment was placed, its corresponding pair of cables was tensioned to support the dead load and ensure proper geometric alignment. The approach spans utilized a combination of precast and cast-in-place concrete girders supported by pile caps and column piers. These sections included integrated infrastructure for lighting, drainage, and utilities. Beneath the deck, seismic isolation bearings and expansion joints were installed to accommodate both temperature movement and earthquake-induced displacements, which were particularly important given the region's seismic profile. On land, extensive roadway realignment was undertaken on both ends of the bridge. This included new interchanges, elevated ramps, and pedestrian pathways. Utilities had to be relocated in coordination with multiple agencies, and temporary detours were constructed to keep traffic flowing during tie-in phases. Intelligent transportation systems were also built into the new alignment, including dynamic signage, cameras, and automated incident detection. A major feature of the new bridge was the incorporation of separated paths for cyclists and pedestrians, physically divided from vehicle lanes by barriers and raised decks. These facilities were not just add-ons, but integrated from the structural design phase, with loads, wind effects, and vibration behavior considered during the modeling of the full bridge system. Universe is now being called the most ambitious project in the history of Universal. Currently, it's under heavy construction, but already blowing minds. The idea for Epic Universe was announced back in August 2019 by Comcast and Universal Parks and Resorts. The goal was to build an immersive theme park experience that goes beyond anything Universal had ever done before. The construction was suspended in 2020, leading to delays, but by early 2022, development picked up pace again. Now in 2025, the site is buzzing. It's a massive 750-acre property located just a few miles south of existing parks in Universal Orlando. This proposed mega project will be the fourth theme park by Universal in Florida, following Universal Studios Florida, Islands of Adventure, and Volcano Bay. But Epic Universe aims to be different. It's being designed from the ground up as a next-generation theme park, integrating technology, storytelling, and infrastructure in bold new ways. The budget for this project is estimated to be over $1 billion. Some reports even suggest it could reach $2 billion with infrastructure costs and land development. There will be at least 4 major themed lands, each with its own entrance. Confirmed so far is Super Nintendo World, inspired by Mario and other Nintendo franchises. Then there's How to Train Your Dragon, a land designed for younger guests with immersive Viking villages and family rides. Dark Universe will be the ultimate one, based on classic monster films like Dracula and Frankenstein, offering a dark, mysterious experience unlike anything else in the park. In terms of construction, the park uses precast, modular structures, concrete slip formers, and high-capacity tower cranes to build quickly and precisely. Tunnel boring machines are digging underground utility paths, and autonomous forklifts are moving heavy materials with minimal human input. The inclusion of modern technology is beyond inspiring. They're using RFID wristbands for access and payments, facial recognition for guest entry, and even AI-powered crowd control systems to monitor and guide foot traffic. This means shorter lines, better safety, and a smoother guest experience. From automated painters handling wall art to 3D printed signage and props, construction is as much digital as it is physical. Even landscaping is being managed by precision irrigation drones and geo-mapped soil sensors. Once open, Epic Universe is expected to draw millions of visitors annually and create over 14,000 jobs, both in construction and ongoing operations. Next up, we have to talk about the Jacksonville Jaguars. Any given day, the Hampton Roads Bridge Tunnel serves as a critical artery for transportation in southeastern Virginia, and expanding this corridor demanded an engineering response of significant scale and complexity. Initiated to alleviate chronic congestion and prepare for growing regional demand, the expansion focused not only on capacity improvement, but also on increasing structural resilience, environmental sensitivity, and long-term operational reliability. The keystone of the project involved the construction of a new twin-tube bored tunnel under the Thimble Shoal Channel, an endeavor that introduced tunnel boring technology to a region traditionally reliant on immersed tube methods. Site preparation began with extensive marine surveying, geotechnical borings, and environmental studies to ensure that dredging, pile driving, and excavation would proceed without destabilizing the existing infrastructure or causing adverse ecological impacts. This was followed by the mobilization of massive temporary trestles and staging areas built along the edges of the Hampton Roads waterway, where precast elements, equipment, and construction materials could be stored and deployed efficiently. Floating equipment such as crane barges, tugboats, and supply vessels formed a coordinated logistics network, essential for moving large-scale items such as precast tunnel lining segments and rebar cages to the offshore tunnel portals. The new tunnels, constructed using a tunnel boring machine specifically designed for the unique soil and hydrostatic conditions of the region, began with the launch pit on one side of the channel. The TBM was assembled on site in a specially excavated pit lined with slurry walls and reinforced with steel bracing. As the TBM advanced, it excavated through layers of clay, silt, and sand, simultaneously installing precast concrete segmental linings to form the circular tunnel structure. Each segment was set in place using hydraulic arms with gaskets to ensure a watertight seal, and the annular space behind the lining was grouted to prevent settlement or water ingress. Parallel to the tunnel construction, bridge widening and interchange improvements on the approach roads were carried out. This required staged demolition and reconstruction of existing structures, new pile-supported bridge spans, and lane realignments. Precast, pre-stressed concrete girders were lifted into place using heavy lift cranes, and cast-in-place decks were poured using travelling formwork systems. The sequencing of this work had to be tightly coordinated with ongoing tunnel operations to avoid disruption to traffic and construction activities. Ventilation buildings, fire suppression systems, and emergency egress pathways were integrated into the tunnel design to meet stringent safety requirements. The mechanical and electrical fit-out included high-capacity jet fans, LED lighting arrays, and a suite of sensors and control systems connected to a centralized monitoring facility. Waterproofing, corrosion protection, and redundancy in utility lines were also built into the system to account for the harsh marine environment. Launch Pacific Plaza in downtown Dallas is one of those rare public spaces that completely shifts how a city feels at ground level. For years, that part of downtown was little more than a patchwork of parking lots, office facades, and narrow sidewalks that people rushed through without stopping. Then came Pacific Plaza, a bold idea to turn a forgotten block into a real urban park, a green space that would invite people to slow down, gather, and actually experience the city in a new way. The park sits along Pacific Avenue, right in the heart of downtown's business district, surrounded by glass towers and busy intersections. What makes it special is how it manages to feel open and calm without being cut off from the energy around it. The designers didn't try to hide the city, they embraced it. You can hear the hum of traffic, see reflections of skyscrapers in the glass around you, and still feel like you've stepped into a pocket of peace. It's a rare kind of balance, one that most urban parks struggle to achieve. Pacific Plaza covers about 3.7 acres, but it feels much larger because of how it's shaped and layered. Instead of one big open lawn, the park unfolds in sections, planted groves, shaded walkways, small plazas, and a central lawn that becomes a gathering point for everything from yoga sessions to lunch breaks to evening concerts. The terrain rises and falls gently, giving the park a natural rhythm that plays off the straight lines of the surrounding buildings. One of the defining features is the massive wooden pavilion that stretches across part of the site. It's a sculptural structure made from warm, curved timber panels that filter light and create patterns of shadow across the ground. It's both shelter and symbol, an architectural gesture that ties the park together while offering shade in the Texas heat. Beneath it, people read, talk, and sometimes even nap, exactly what a good park should make possible. The project was also a victory for adaptive use. Much of the land that became Pacific Plaza had been surface parking for decades, a dead zone in the middle of downtown. Turning it into a park wasn't just about beautification, it was about reclaiming valuable real estate for public life. The transformation reconnected nearby buildings and opened up pedestrian routes that had been blocked for years. It gave downtown workers a reason to go outside during the day and residents a place to gather in the evenings. The materials are simple but durable: stone, wood, native grasses, and trees that can handle the Dallas climate. Everything about it was built with longevity in mind. Drainage systems are hidden beneath the surface. Lighting is integrated into the landscape, and maintenance was designed to be efficient rather than ornamental. It's a park meant to last, not one that needs constant upkeep just to look presentable. When you stand in Pacific Plaza today, you can feel how it changed the dynamic of downtown. It's no longer just an office district, it's becoming a livable one. Families stop by with kids, cyclists cut through on their way to Deep Ellum, and the place fills with a steady hum of life. Let's travel over to China, where the Shanghai Tower pierces the sky at 632 meters. This twisting, glass-clad giant is the tallest building in China and the third tallest in the world, second only to the Burj Khalifa. Located in the heart of Lujiazui, Pudong, this architectural marvel is a symbol of China's rapid growth, innovation, and sustainability. Construction of the Shanghai Tower began on November 29, 2008, and the exterior was completed by 2015 with an estimated cost of around $2.4 billion. The tower officially opened to the public in 2016, designed by the international architecture firm Gensler, with Shanghainese architect Jun Xia leading the project. The tower was envisioned as a beacon of modern urban development. What makes the Shanghai Tower truly stand out is its twisting, spiral design, which reduces wind loads by 24%, significantly improving structural stability. This design choice helped reduce the need for excess construction materials, saving an estimated $58 million in costs. The building consists of 128 floors above ground and 5 basement levels, housing offices, luxury hotels, observation decks, and retail spaces. Its observation decks, especially on the 118th and 119th floors, offer breathtaking views of the skyline of Shanghai. The double-skin glass facade of Shanghai Tower acts like a thermal blanket, enhancing energy efficiency by minimizing the need for heating and cooling systems. Between the inner and outer glass layers, there are 9 indoor atriums, which serve as sky gardens, adding a touch of greenery amidst the clouds. One of its most futuristic features is its vertical transportation system. The tower held the record for the fastest elevator in the world until 2017, reaching speeds of 20.5 meters per second. Manufactured by Mitsubishi Electric, these elevators whisk visitors from the ground floor to the top in under a minute. As the largest LEED Platinum certified building globally, the Shanghai Tower showcases advanced sustainability features. It uses rainwater harvesting systems, wind turbines, and geothermal energy to reduce its carbon footprint. In 2021, it also became home to the highest hotel in the world, the J Hotel, on its 120th floor. The top of Shanghai Observation Deck, located on the 121st floor, offers breathtaking panoramic views of the city. Overlooking the Peace River in northeastern British Columbia, the Southside Dam emerged as the third major hydroelectric development on this river, following the Wack Bennett and Peace Canyon dams. Planning for this project involved decades of studies, regulatory reviews, and public consultation before actual construction began in the mid-2010s. Once approved, the first phase of construction focused on site clearing and access preparation. This entailed removing thousands of hectares of vegetation, felling trees, building new access roads, and reinforcing existing ones to accommodate the massive flow of equipment and personnel. Additionally, geotechnical investigations were carried out early to determine subsurface characteristics, which were critical for designing stable foundations in a valley known for its complex geological conditions. Foundation excavation proceeded next, with crews stripping away overburden to expose competent bedrock. This phase involved the use of heavy earth-moving equipment such as hydraulic excavators, bulldozers, and articulated dump trucks, operating on a meticulously choreographed schedule to avoid bottlenecks. Extensive rock bolting and grouting were performed to stabilize the slopes and ensure that water seepage through the foundation would remain within allowable limits. At the same time, river diversion tunnels were being bored through the north bank. These twin tunnels, each several hundred meters long and several meters in diameter, were lined with reinforced concrete and designed to carry the full volume of the Peace River during the dam's construction phase. Once river diversion was in place, the main earth-filled dam structure began to take form. This embankment-type dam required the placement of millions of cubic meters of material in zoned layers, each serving a specific structural or impermeable function. The dam's core consisted of compacted clay designed to be nearly watertight, while the outer shells were built from gravel and rockfill for strength and stability. These layers had to be placed with extreme precision, both in terms of moisture content and compaction density, using a fleet of high-capacity vibratory rollers and GPS-guided dozers. Simultaneously, the powerhouse and spillway complex were under construction on the left bank. These concrete structures demanded an entirely different set of construction techniques, beginning with the erection of massive cofferdams to dewater the work area. Tremie concrete was often used for underwater placements, while large tower cranes and high-capacity formwork systems enabled continuous vertical construction. The powerhouse was designed to house 6 large Francis-type turbine generator units, each requiring massive steel components that were fabricated off-site and transported in modules. Beyond the physical structures, a network of transmission lines was installed to carry the electricity generated at Site C to the provincial grid. These high-voltage lines required the erection of steel lattice towers across challenging terrain with careful coordination to avoid environmental and cultural sensitivities. Environmental mitigation was a persistent theme across all stages of the project, involving fish habitat reconstruction, wildlife corridor planning, and ongoing monitoring of water quality and sediment levels. Work on the Hampton Roads Bridge Tunnel expansion begins with one of the most critical early tasks in any marine tunnel project: creating the staging and assembly areas for the massive tunnel boring machine that will carve out the new immersed tube sections. In this case, engineers first established a large-scale construction platform on artificial fill, extending from the shoreline to provide space for equipment, materials, and prefabrication activities. This required precise dredging and placement of engineered stone bedding to resist scouring from the strong tidal currents of the Chesapeake Bay. The logistics here are challenging because the site sits in an active shipping channel, forcing contractors to coordinate vessel movements and keep the navigation lanes open at all times. Once the staging area was ready, attention shifted to the launch pit for the tunnel boring machine. This involved driving reinforced steel sheet piles deep into the seabed to create a watertight cofferdam, followed by controlled excavation down to the required depth. Inside this pit, a concrete cradle was constructed to support and align the TBM's shield during launch. Simultaneously, a similar receiving pit was prepared on the opposite island to ensure the boring process could conclude without risk of misalignment or water ingress. On the marine side, barges and cranes were mobilized to handle the delivery and installation of precast tunnel segments. Each segment, manufactured onshore under strict tolerances, was brought out and lowered into place by specialized lifting frames, then joined with gaskets and bolted connections to ensure a watertight seal. These operations often had to be timed to coincide with favorable tidal conditions and minimal wind to prevent lateral movement during placement. Above the waterline, expansion of the approach trestles and bridge spans was tackled. New steel girder spans were fabricated and barged in, then lifted into position using floating cranes capable of handling hundreds of tons. Deck panels, consisting of precast concrete units with embedded reinforcement, were set into place, post-tensioned, and topped with a high-performance asphalt overlay designed for heavy traffic and coastal weather resistance. Inside the tunnel, after excavation, workers installed precast segmental liners, each fitted with embedded waterproof membranes. As sections were completed, the annular space between the liner and the excavated ground was pressure grouted to provide stability and prevent settlement. Mechanical, electrical, and safety systems were installed in parallel. This included fire suppression piping, LED lighting arrays, jet fans for ventilation, and a fully integrated monitoring network capable of detecting structural movement, water infiltration, or hazardous gases. A major engineering hurdle throughout was maintaining traffic flow on the existing bridge tunnel. Temporary lane shifts, stage closures, and floating work zones were used to minimize disruption. The expansion also required reinforcing the existing island structures to support the new tunnel portals and approach roadways, which involved deep foundation piling driven through variable soils ranging from loose sands to dense clays. The Howard Franklin Bridge Expansion, a mega project that's reshaping Tampa Bay in real time. If you've ever driven between Tampa and St. Petersburg, chances are you've crossed the Howard Franklin Bridge. It's one of the most traveled bridges in Florida, carrying nearly 180,000 vehicles each day across Old Tampa Bay. For years, locals have dreaded the traffic jams, bottlenecks, and delays on this vital link. The current structure, built in 1959, has long been overdue for an upgrade. That's why the Department of Transportation in Florida launched this massive expansion project to bring safety, capacity, and resiliency to this crucial corridor. The project officially kicked off in 2020, and in 2025, it's hitting a critical phase. The work involves building a completely new parallel bridge structure just south of the existing one. This new bridge will carry 8 lanes, 4 in each direction, including express lanes, general use lanes, and a dedicated multi-use path for pedestrians and cyclists. When completed, the older 1960s bridge, currently northbound, will be demolished. The newer southbound span, built in 1990, will be converted for northbound traffic. In short, you'll have 2 modern bridges, both equipped for today's traffic volumes and tomorrow's needs. The budget for the project is approximately $865 million. It's being funded by the Strategic Intermodal System, which focuses on infrastructure critical to the movement of people and goods. Construction techniques on this bridge are state-of-the-art. Teams are using floating cranes, barges, and pile-driving rigs to install more than 3,000 concrete piles deep into the bay floor. These piles form the foundation of the superstructure of the new bridge. Girders are precast off-site and shipped to the project via barge, then lifted into place with massive gantry cranes. Each girder weighs over 100 tons. The bridge deck is formed using pre-stressed concrete segments, allowing for rapid assembly and minimizing disruptions to existing traffic. The construction teams are working under strict environmental guidelines to protect the sensitive ecosystem of the bay. Special silt curtains and turbidity barriers are being used to prevent sediment from spreading. The bridge is being designed with elevated clearances to help protect against future sea level rise and storm surge events. Howard Franklin Bridge is a lifeline between 2 of the fastest growing cities in Florida. It supports commuters, tourists, freight trucks, and emergency responders. Once finished in 2026, the new bridge will reduce congestion by up to 50%, cut travel times, and provide hurricane-resilient infrastructure that can keep Florida moving, even in a crisis. Let's talk about the above the Austin skyline. This super tall, mixed-use tower was designed to house residential, hotel, and commercial spaces, each demanding unique structural, mechanical, and architectural systems. From the start, the complexity of the project required an integrated delivery strategy, coordinating trades across multiple tiers of vertical development. The foundation work was executed using a deep mat foundation system resting atop drilled piers that penetrated through layers of expansive clay and limestone. These piers, reinforced with heavy rebar cages and cast with high-strength concrete, ensured load transfer to competent subsurface strata. Given the high axial loads generated by the structure's extreme height and mixed occupancy, foundation design factored in both static and dynamic load profiles, especially wind-induced sway. The structural core was formed using a jump form system that climbed the building's height in sync with floor plate construction. This core housed elevators, stairwells, and mechanical shafts, and was built ahead of the floor framing to provide lateral stability. Post-tensioned concrete slabs were used for floor systems, allowing thinner profiles and greater span efficiency, which proved essential in maximizing usable floor area within the tower's tight footprint. Each floor cycle was optimized to a typical 7-day pour schedule, with concrete deliveries, formwork setting, rebar installation, and MEP rough-ins following a tightly choreographed sequence. As the tower rose, the staging and material hoisting strategy became critical. A tower crane, climbed in sections and anchored periodically to the core, provided primary lifting capacity. Specialized buck hoists were installed to move labor and materials vertically without interfering with crane operations. Material prepackaging at ground level and just-in-time deliveries helped alleviate congestion and minimized the need for laydown areas in the restricted downtown site. The facade system combined curtain wall glass with custom metal panels, unitized off-site to improve installation speed and quality control. Each panel incorporated embedded anchors and pre-installed glazing, which were then hoisted and set using monorail systems mounted to the slab edges. Swing stages and temporary platforms allowed facade crews to operate in tandem with interior fit-out teams, maintaining the aggressive construction schedule. Mechanical, electrical, and plumbing systems were designed with vertical zoning to accommodate the different occupancy uses within the building. Separate HVAC risers, fire protection loops, and electrical buses were installed for the hotel, residential, and amenity levels. Mechanical floors at designated intervals housed air handling units, booster pumps, and switchgear, allowing for pressure brakes and maintenance access. Noise and vibration isolation pads were installed beneath equipment to prevent transmission into living spaces. Fire safety and life safety systems followed high-rise standards, including pressurized stairwells, fire-rated refuge areas, and integrated smoke control systems. Backup power generation and emergency communication panels were installed to meet code and provide operational reliability.